In this video, you will learn how to use the Raylib library by making a 2D and a 3D game. Raylib is a powerful module that has become super popular over the last few years because it makes it very easy to create more advanced games without having to rely on a game engine like Godot or Unity. It has a huge community and lots of available resources. If you just want to get into game development, Raylib would be an excellent choice. It shouldn't take you long to make something more advanced like Doom or Pokemon. For this tutorial, I will use Python, but Raylib is available for a lot of languages, and the tools are standardized, meaning with some modifications, you could probably follow along in another language. For the itinerary of this video, we will first cover all of the basics and 2D stuff. Then we make a 2D game, after that we cover 3D basics, and then we finish things with a 3D game. That way you learn how to organize your games, and you get dedicated recipes for things like movement and input, 3D models, cameras, animations, collisions, and so on. That being said, to make really good games, you want to have a strong math foundation, which goes beyond this tutorial. If you want to learn that though, check out the sponsor of this video, Brilliant. They offer interactive and incredibly well-made tutorials on a lot of subjects vital for game development, like vector math and algebra. All of the lessons are super engaging and highly interactive, which makes the learning process much more fun and effective than just reading a book. For every subject, you can start from scratch or jump right into a course. Either way, you will get to a competent level fast because you get digestible chunks of learning that you can practice and master before continuing. You can access Brilliant from your computer or via an app. It's super accessible. So instead of wasting your time on TikTok or Twitter, you can build a powerful habit that will make you a more competent person. So check it out at brilliant.org/clearcode. You will get a 20% discount and the first 30 days are free, meaning there's not much to lose. Also, by signing up, you help me make more of these videos. Before we get started with actual coding, we need to cover how games work on a fundamental level. Don't worry, this won't take long. In the most basic sense, a game is just an interactive movie, meaning that, like in a movie, you are drawing a lot of images in a sequence. The only difference is that for a game, each image is created dynamically, while images in a movie are static. In practice, this simply means that we are creating a while loop, and on each iteration of that loop, we first update the game, meaning we check for user input, update the position of the player and the enemies, check for timers and items, etc. Once we have that, we know where all of the elements are supposed to be, which means we can draw the actual image. If we keep on doing that fast enough, we have a game. Because of that, Raylib also doesn't need to do that much. The core functionalities of the module are displaying images, text, and 3D models, checking for user input, and playing sound. Beyond that, it also offers some extra parts like cameras, checking for collisions, or drawing shapes. But those are fairly minor. In fact, the best resource to learn Raylib is the cheat sheet on their website, which is basically the documentation. This one covers the entirety of the module, and I would very much recommend to have this open while you do anything. It is incredibly useful. Although for Python users, keep in mind that this document was written for the C languages, meaning everything is in Pascal case. To convert that to Python, you simply have to use snake case, which is super easily done. Beyond that, other useful resources are ChatGPT and the Raylib Discord server, which tends to be super helpful. Two more things that we need. Number one, you have to install Raylib. The official name of the Python module is called Raylib, and you install it by opening a terminal and type pip install Raylib on Windows and pip3 install Raylib on Mac. That's all you need for this part. Number two, there are project files that I am going to start with. This will contain all of the images, sounds, and a couple of template files. You can get all of these files from GitHub or Google Drive. Just check the video description. Download the Start Resources folder, which is going to contain 4 subfolders. And for now, we are only going to need the Basics folder. Open that one in the code editor of your choice. For this tutorial, I am going to be using VS Code, but any code editor is going to work, as long as it can run Python. Let's have a quick look what we are working with. There are 2 folders, Assets and Code. Inside of Code, we already have a bunch of Python files. The first one is entirely empty, but then later on, we have a few starting things. That way, you don't have to watch me type for too long, but I will explain all of this as we go along, so don't worry too much about it. Besides that, inside of Assets, we have a couple of music files, a PNG, a font, and inside of animations, a cowboy walking animation. Alrighty, so let's get started. And the first thing I want to do is number one, create a window, and number two, draw on this window. There are three things that I want to draw: basic shapes, text, and images. While we are here, we can also work with basic colors, but that shouldn't be too difficult. For all of that, here we are back in VS Code, and right now I am in onebase.py, which at the moment is entirely empty. The first thing that we are going to need to use Raylib is to import it, which we are doing by the import from pyray import everything. This will give us all of the methods and functionalities of Raylib. On top of that, you also want from Raylib import everything. This Raylib module contains all of the constants that you might need, for example, colors and keyboard bindings. Once we have all of that, we want to create a window, which we do with init underscore window, which wants three arguments: the window width, the window height, and the window title. In my case, I want to create a window that is 1920 pixels wide, 1080 pixels tall, and has a window title of, let's call it base. This should give us a window, meaning if I run the program now, we can see a window for a very short amount of time. And that is intended. The issue we have at the moment is that we are importing things, then we are creating a window, and then we are finishing the code, meaning the window we created disappears. Meaning we need some kind of functionality to keep all of this open permanently, which in practice means we want to have a while loop. You could simply go with while true, that would be kind of possible, but a better way inside of Raylib is while not window should close. And don't forget to call this one. Later on, we can manipulate the return value of this function very easily, which makes it ideal to control if the game should stay open or if it should be closed. Inside of this while loop, we want to run two functions: begin drawing and end drawing. This is going to give us a drawing loop that is important for Raylib. Between these two functions, we are doing all of the drawing of the game, which we will work on in just a second. First of all though, one more thing that you want is after the while loop, you want to close the window, which is basically the opposite of init window. Now this function isn't strictly necessary. It's simply good practice after you have initialized everything to uninitialize things, which sometimes can prevent an error, and generally it's just one line at the end of the program that you should be calling. Anyway, with that, we basically have a while loop in which we are drawing some basic things. Once we have that, we are getting a window that stays open permanently. That's a pretty good start. Now, to actually do something with it, you want to work inside of the drawing bit, meaning after begin drawing and before end drawing. The easiest method you could be calling here is called clear background. This one draws over the entire screen with a plain color. As an argument, it wants to have a color that you want to use. There are quite a few constants that you are getting from Raylib. For example, you could go with black in here, but that's the default that we have already used, so this doesn't do very much. To actually see something, you could instead use something like red in here, and then you're getting a red color. To see all of the options, you want to go to the Raylib documentation, and you can find the colors all the way at the bottom. So scroll for quite a bit, and there at the bottom, you can see the colors. In my case, I have used red and black down here, but you could use any of these colors. Besides that, if you look a bit further to the right, you see more color information. This is an RGBA tuple. In case you don't know what that is, let's talk about it really quickly. When it comes to colors inside of Raylib, you have all of the inbuilt color constants, like black, white, red, yellow, and so on. Besides that, you can define custom color values using an RGBA tuple, which basically means that you're defining a red, green, and blue color along with an alpha value. And all of these values are between 0 and 255. For example, 255, 0, 0, 255 will give you a pure red. 255, 255, 0, 255 will give you a pure yellow. And then if you set 0 for the alpha value, you're always getting an invisible color because you have no alpha values. So for example, back in the documentation, if you look at the red color, we have a lot of red, we have very little green and blue, and we have the full amount of alpha. As a consequence, we're getting a red color that isn't too strong. And back inside of Raylib, besides red, you could use a simple tuple with, for example, 255, 0, 0, and 255 to get a pure red color. If I run it now, we're getting a stronger red. If I change this to 0, 0, 255, and 255, we're getting a blue color. With that, we have basic colors inside of Raylib. It's ultimately fairly simple. And in my case, for the background color, I want to stick with black because that one is fairly neutral. With that, we can start working on drawing actual shapes, which is done with a few methods that you can find in the documentation. Here we are, and at the moment, we are looking at module R-Core, which gives you access to core functionality. For example, init window and close window and window should close. The functions that we have already seen. If you scroll down to the second section, R shapes. This gives you access to drawing functionalities. For example, in there, you get basic shape drawing functions. The simplest one is to draw one pixel, for which Raylib is expecting a position for X, a position for Y, and a color. Let's try that one. After we are clearing the background, I want to call draw pixel. And now I have to insert a position for X, Y, and a color. Let's set 100 pixels for X, 200 for Y, and for the color, let's choose something simple, red. If I now run the code, this is going to be quite hard to see, but if you look very closely, we have a red pixel here. I guess what we could also do is another function, draw circle. For this, we want to have 4 arguments: center X, center Y, radius, and color. Let's say I want to go 400 pixels on the x-axis, 200 pixels on Y. For the radius, I want to go with 10 pixels, and for the color, let's go with green. Now if I run out of this again, they can see it much better. We now have a green circle a bit to the right of the red pixel we have just drawn. So those are the basic drawing functions inside of Raylib that allow you to draw basically any kind of shape. If you look at the entire list, you can find pretty much any kind of shape. The more complex the shape, the more arguments are expected. Should be fairly straightforward. That being said, there's one thing I want you to think about. If I run this again and move the window to the side, for this circle, we have set X to 400 and Y to 200. How does this get us to this position here? Or in other words, what is our starting point? The way you want to think about it is that the window is a coordinate system. Our window at the moment is 1920 pixels wide. That is this dimension here, 1920. Besides that, the window is 1080 pixels tall. That is this side, 1080. And this would be our coordinate system in which we can draw. Really important for all of this, the origin point is in the top left. This will be position 0 and 0. This means to get to this point, we are moving 400 pixels to the right, or this distance here, and then we are moving 200 pixels down, which would be this distance here. With both of those, we're getting the center of the circle. This should be kind of familiar because in high school, you probably worked with a coordinate system that looked something like this. You had an x-axis and a y-axis with the origin point in the bottom left. In Raylib and most of game development, we have a similar system, except that the y-axis is inverted. If you want to go to the right, you want to increase x. And if you want to go up, for Raylib, you have to decrease y, which does feel a bit counterintuitive, but for most game development frameworks, this is the default. And just to demonstrate all of this, this is our x position and this is our y position. If I set both of these values to 0, we should be in the top left. And we are. You can now see in the top left of the window, we have 1/4 of the green circle. I guess to make this a bit more visible, let's make this much larger. they can see the circle in the top left. And the larger x becomes, let's say 100, the further to the right we go, and the greater y becomes, the further down we go. If I make this number negative, we cannot see the circle anymore because it's now on top of the window, meaning the circle would be roughly here. If I change this to negative 50, we can see just a bit of it. So with that, you should be able to draw basically anywhere on the window, which means we can go a bit deeper into the drawing functions. Once again, here we have all of them, and what you see very often is that you have a basic drawing function and then variations of it. For example, we have draw pixel and then draw pixel v, which wants to have a vector for the position, or more specifically, a vector 2. Just in case they are new, let's talk about vectors for just a second. In the most basic sense, vectors are basically a list with a limited set of numbers. We have a vector 2, which has an x and a y value, and a vector 3, which has an x, y, and z value. These values are stored as floats, and you can both access and change them. To directly address them, you would do something like vector2.x, y, or z. In game development, vectors are a really easy way to store something like position or directions. On top of that, they also have lots of useful math functionalities. Because of that, you see them all the time. Which means, back inside of the code, besides draw pixel, we also have draw pixel v. This wants to have two arguments, a position, which has to be a vector 2, and a color. To create a vector 2 in Raylib, you simply want to type vector 2, and then you have to specify an x and a y value. I guess we can put this pixel right next to the original pixel that we have drawn. Which means for the position, I want to have 101 for x and 200 for y. After that, for the color, let's go with blue. If I now run this again, this is going to be very difficult to see. I guess we do need a bit more distance between the two. Let's go with 200 and 200 and make this pixel white. Then you can see this is quite difficult to make out, but there we have a white pixel, which we have positioned using a vector 2. And once again, to make this a bit more visible, you have a similar functionality for draw circle, meaning we can call draw circle, and if you now add an underscore, you get quite a few different options. The one I want to go for is draw circle v, for which, once again, we want to have a center position that is now a vector 2, and then we need a radius and a color. For the position, once again, I want to create a vector 2 and place this one at 1000 and let's say 600. After that, we need a radius, let's go with 200, and finally, we need a color, something we haven't used yet, yellow. I can now run this again, and we're getting a big circle in the center-ish of the window. For this one, we're going 1000 pixels from the left, meaning this distance here, and we are going 600 pixels down, something like this, which is then giving us the new center of the circle. And alrighty, with that, we have basically all you need to know for the basic drawing functionalities. There's just one more thing that I do want to cover. Let's say I put these two circles in the same position, meaning they should both be on position 1000 and 600. What do you think is going to happen? Well, if I run this, we can only see the yellow circle, but we cannot see the green one. So what happened here? And if you think about it, I think you can see the problem. Raylib is drawing all of this in order, meaning we first draw this pixel, then we're drawing that pixel, then we are drawing the green circle, and finally we are drawing the yellow circle. Since those two circles are in the same position, and the yellow circle is much larger than the green one, we are drawing the yellow circle on top of the green one. Or in other words, the green circle is behind the yellow one. If you flip those two lines around and draw the green one after the yellow one, then you can see both of them. Which basically means that you want to be really careful about the drawing order. This one is super important. If you call a function after another, then the later function will be drawn on top of the previous one. So with that, we have quite a few basics. Let's do an exercise. I want you to draw a line from position 0, 0 to to 500 and 200. This line should be a really dark red color, which means you have to define a custom RGBA value. On top of that, the line thickness should be 10 pixels. Pause the video now and figure this one out on your own. To get started with this exercise, I would recommend to look at the documentation and then go once again to the drawing functions. This one contains a whole bunch of draw line functions. Since you want to define the width of the line, you want to look for something like a line thickness, which you do not have in drawLine or drawLine V. But you do have drawLine X, which has a vector to starting position, a vector to end position, a thickness, and a color. Exactly what we need. Which means, back inside of the code, I want to draw line X, for which I want to have a start position, a vector 2, with 0 and 0. For the end position, I want to have a vector 2 that I believe was 500 and 200. Next up, we want to have a line thickness, which I want to set to 10. After that, finally, we will need a color, which I want to be really dark red, for which we need a tuple with a very low amount of red. Let's go with 50. Besides that, I want to have 0 for green, 0 for blue, and 255 for the alpha value. If I now run this again, we are getting a really dark red line that goes from 0, 0 to 500 and 200. Cool, I hope that wasn't too difficult. If you could do the exercise, drawing basic shapes should be fairly straightforward at this point, which means we have custom shape drawing covered. Most of the time though, this is not what you want to do. For basically any game, you want to import and display images. And for that, if you look at the assets folder, there we have spaceship.png. This image I want to import and display. For that, first of all, we have to cover the import. This has to happen before we are doing the while loop. Simply because we only have to import the graphic once. The function that you want to look for is called load_texture, for which Raylib is expecting a file path. And in my case, within VS Code, the starting point for the path is the root folder. From there, I want to go to assets. After that, we have spaceship.png. And really make sure that you are spelling all of this correctly. With that, we have a texture. This I want to store inside of another variable. Let's call it spaceship_texture. To draw it inside of the drawing bit, you simply have to call draw_texture, which first of all wants to have a texture, which in my case is spaceship texture. Then we need an integer for x and y. I guess for now, we can use 0 and 0 to have the ship in the top left. Finally, we have tint color, which most of the time you want to be white. I'll talk about this one a bit more in just a second. First of all though, if I run the code, you can see the ship in the top left. Now, while doing all of this, there are two important things to understand. Number one, when we work with images, so any kind of PNG or JPEG file, we always have a rectangle. For the ship, it would look something like this. That's the actual size of the image, where we have visible pixels in the middle, that's the ship, and then we have invisible ones around it, which you can largely ignore, but they are there. Besides that, the other important thing is that when we place a texture, we always place the top left. This would be position 0 and 0. For the tint color, white is the default, and this one doesn't change the color at all. But if you use something like blue in here, then you're multiplying every single pixel with a custom color, which can sometimes be a nice effect, but most of the time you want to have the graphics by themselves, for which you want to have a white tint color. And well, that's basically it. If you want to display an image, you want to load a texture and then draw the texture. For more information, you want to look at the documentation. For that, you have to go down quite a bit more. You have to go beyond shapes and go to R textures. In there, if you go a bit further down, you have texture drawing functions, where you have draw texture V, draw texture X, and so on. All of these draw a texture with some slight variations. Now, before we continue, I want to cover some very minor import issues. Depending on the operating system, the path should either contain a forward or a backward slash. And you want to be flexible so your game runs everywhere. Or in other words, when we are loading the texture for the file path, I'm having a forward slash. I could change this to a backward slash and the game would still run fine, but this isn't a given. I want Python to dynamically create the proper path so we don't have to worry about it. It could, for example, happen that on macOS, you need to have a specific kind of slash, and if you don't have that one, the graphic will not be found. That would break your game pretty badly, and you want to avoid that. To fix that, we can use an inbuilt Python function, which you have to import first of all. You want from os.path import join. Join connects a couple of strings with the right slash. The way you would use it, and let me print the result. You want to call join, and then the nodes you want to go through. In my case, to get this kind of path, I want to go to assets, and then as the second argument, I want to get spaceship.png. If I now run this, we are printing assets spaceship.png with a backward slash, the same we have here. The difference now, though, is that this path is appropriate for the operating system. Which basically means you simply want to get the join method and then use it to create the file path. The end result is going to be the same, and this issue most of the time is not going to be too important. Most operating systems are quite flexible. But in some rare cases, this could avoid your game from crashing, which is why you should probably generally include it. That covers the first issue. The second one is that depending on your code editor, you want to be really careful about the root folder. In VS Code, the path always starts at the root folder. But in something like Sublime Text, you are starting at the Python file. Or in other words, if I have the same code in Sublime Text and run it, we cannot see the ship. And on top of that, Raylib is giving us a warning that it cannot find the spaceship file. That is because for the path, Sublime is starting in this Python file, which in practice means you first want to go up one folder, which you do with double dots. Then you can go to assets and then you can go to spaceship. If you now do this again, we can find a texture once more. In practice, if the import doesn't work for you, check about the specifics of your code editor. That's probably the issue. In my case, I am going to use VS Code for the entirety of this tutorial, meaning the start of the path is always the root folder. Perfect. With that, we have the textures covered. That wasn't so difficult. That being said, there's another minor complication that you might have noticed if you read the documentation. In there, we can draw a texture and we can load a texture. But if you go up just a bit, you can also see images. Which begs the question, what's the difference between an image and a texture? Textures are loaded directly into the GPU memory. This one is called VRAM. From there, we can directly draw them, but we cannot change them anymore. Images, on the other hand, are loaded into the CPU memory. This is the RAM. Before they can be drawn, they need to be converted to a texture, meaning we are loading them into the GPU. But before we are doing that, we can make changes to them. Let's say I want to create a spaceship image, which we are getting via load_image, for which, once again, we will need a file path that I want to create using the join method. I can simply copy the line we have already used for the spaceship. This is now giving us an image, which we cannot display right away, but we can manipulate it. For that, you want to look at image manipulation functions. For example, in there, you could resize the image, you could rotate the image, you could give the image a color tint, invert it, or create a grayscale, and so on. The way that would work is you want to call image color grayscale and pass the image in there. In my case, spaceship image. That way, this image would be black and white only. And to display it, you have to convert this new image into a texture. For that, I want to create a new texture variable and then call load texture from image, which wants to have an image as the only argument, which in my case is the spaceship image. This new texture we can now display like we have done with the original texture. I guess now for some variation, we could use draw texture v, use a vector2 for the position. The texture I want to display is the new texture, and the position could be a vector2 with 100 and 0. We will still need a tint color, and I want this to be white. Now we can run this again, and next to the original ship, we have the same thing, except now it's a grayscale color. That is pretty much it for displaying images and textures. It doesn't get that much more complicated. You simply have a whole bunch of functions that you could be using to manipulate the image. To practice all of this, let's do an exercise. I want you to import one of the cowboy images. Those are inside of the animations folder. Invert the colors of this image and then display it in the bottom right of the window. Pause the video now and see how far you get. Let's have a look at the cowboy image. You want to go to Assets, there we have Animation, and in there you have, for example, 0.png. This gives you one cowboy image, which we want to import. Also, it doesn't really matter which one you import, they all look fairly similar. I want to create a cowboy image, for which we want to load the image via the join method. I want to go to Assets, then I want to go to Animation, and finally 0.png. This would give us the image, which we then want to convert to a cowboy texture via load texture from image with the cowboy image. This texture we can now display, which we are going to do down here. I want to draw texture with the cowboy texture, and to get into the bottom right, for the X position, I want to go with 1800, and for Y, let's go with 900. Finally, for the tint color, I want to have a pure white color. That way, in the bottom right, you can now see the image of the cowboy. That's a good start. Besides that, I want to invert the colors of this image, for which I can use image, color, and invert with the cowboy image. If I try this one, in the bottom right, we have the cowboy with the colors inverted. Perfect. So with that, we have images and textures. That's pretty much it. Which means there's just one more thing that I want to cover, and that is going to be displaying text, which in the most basic sense is fairly simple. Draw underscore text, for which you need a string, let's say some text. Then you need an X and a Y position. I guess we can stay on the left side of the window, 0, and go down a bit, 400. Then we need a font size. Let's go with 100. That is going to be quite large. And for the color, I want to go with pure white. Let's try this again. And there we get some text in the default font with a font size of 100. This would be the easiest way to display text inside of Raylib. For more information, once again, you want to look at the documentation, scroll down, and at some point, you will find our text. And there, you have all of the text functions that you are going to need. The one I have just used is called draw text, a fairly simple one. That being said, there is an even simpler one called draw FPS, which simply draws the current frame rate, which we don't need at the moment, but is going to become important later on. I'll get back to it. For now, there's one more important thing that I want to cover. What if we want a custom font? Inside of draw text, we cannot use that. But for example, inside of draw text X, we can set a custom font. Although for that to work, we first of all have to import a font. This happens before the while loop. I want to import a font. And I guess for proper comments, I want to import images or textures first of all. And after that, for the font, I want to create a new variable called font. To get a font, you want to call the function loadFont, which only wants to have one argument, a file path, which we are creating via the join method. Now for the file path for this one, I want to get 0hour.otf, which we can find inside of assets, and then we have 0hour.otf. This would give us our font. And after we have that, I want to call draw text x, for which we will need the font file we have just imported, font. Then we need text. Let's call it some more text. After which we need a position, vector 2 with 0 and 600. For the font size, let's go with 20. Next up, we need font spacing, which I want to set to 0. And finally, we need a color. Let's go with blue. If I now run the code, we are getting some more text a bit below the original text. That's pretty much all you need here. Cool. With that, we can import images, textures, and a font, and display all of that. A fundamental part of any video game is movement, which is what we are going to cover in this section. By the end of it, we have a ship bouncing around the screen. In the most basic sense, movement is fairly simple. You simply draw an image in a different position. And this would also work for a shape or a text. It doesn't really matter, but images make the most sense. If this change in position happens gradual enough, it will feel like movement. Let's do a demonstration. For that, I have a new Python file. This one is called to_move.py, in which we are doing nothing new. We first do all of the basic imports, then we set up the window and import the ship texture. This we are then using inside of a drawing loop, all of this, which at the moment clears the background with a black color and draws the texture. For that we have position X and position Y, which we are defining up here, position X and position Y. The end result is going to be a ship in the top left, because our position X and Y are both 0. If you manage with the first part, none of this should look complicated. Anyway, what we can now do, before we are drawing, we can do some updates. And after we have done that, we are doing the actual drawing part. For the updates, all I want to do is position X plus equal 1. If I now run this game, the ship is going to move to the right, although it's really, really fast. But we have movement nonetheless. That's really all we are doing in the most basic sense. That being said, we have a couple of minor complications that you want to be aware of. First of all, you want to store precise data, which effectively means that you want to use floats instead of integers. Besides that, another important thing is that we are just drawing over the previous frame. We don't discard it, which sometimes can give you some weird results, but it's very easy to fix. The one issue that does require a bit more theory is frame rate independence, or in other words, the frame rate of the game can mess with movement quite a bit, which you want to be aware of. That is going to be the most extensive part, but let's start with the easier ones. We want to store precise data, and we want to make sure that the last frame is not visible anymore. This part we can actually start with because it's super easy to display. Back inside of the code, when we are drawing everything, we first fill the screen with a black color, and then we are drawing the ship wherever the X position happens to be. But now let's see what happens if we don't clear the background with a black color. And run all of this again. We are getting some really weird behavior. What happens here is that we can see all of the previous frames, and we simply draw another frame on top. We never fill the entire background with a black color. As a consequence, the game is going to look really funky, and in basically all instances, you do not want to do this. So pretty much for any game, always clear the background, unless you very specifically do not want to do that. If you're doing that though, you're getting movement again. So this is much better. That's the first issue. The second one is that we want to store precise data. At the moment, the ship is going really fast. We are moving by a unit of 1 on every single frame of the game. Or to be a bit more specific, On every iteration of this while loop, we are moving the x position a bit further to the right. Since we have a ton of frames, this movement is really fast. But if I set this to 0.1, we're getting an error because draw texture wants to have integers for the position, meaning we're getting a type error that an integer is required. This is simply the nature of draw texture. It always wants to have an integer, but in our case, since we want to move much slower, this isn't ideal. As a consequence, this draw texture shouldn't be used for anything moving. A much better alternative would be draw texture v, where we are using a vector for the movement. And the way that would be working, I don't want to have position x and y anymore. Instead, I want to have a ship underscore position, which is going to be a vector 2 with 0 and 0 by default. This position we are then using inside of draw texture, meaning instead of position x and y, I want to have the ship position. After that, we also don't need position.x plus equal 1 anymore. If I now run this again, we have the ship in the top left position. And now to move it, I simply want to get the ship position and then target the x part of the vector and increase it by, let's say, 0.1. If I now run this again, we have the ship moving, although it's moving at a very inconsistent speed. That we will fix in just a second. For now though, this is the kind of movement system that you actually want to use, where you have a vector position and then you target x and y in the 2D space of this vector to move a texture, or rather you are drawing the texture in a different position. Which is a good start, but in practice, this still doesn't look ideal because this ship is moving super inconsistently. That happens because of the frame rate, which we can actually display. I talked about this just a second ago. We can draw the frame rate that we currently have, for which we need an x and a y position. Let's go with 0 and 0. If I now run this again, in the top left, this is quite small, but you can see the frame rate, and this one changes, which is kind of an issue. Effectively, on every cycle of this while loop, we are updating the position, meaning if this runs faster or slower, we're getting a different movement speed, which for a real game is going to be a headache. This is something you absolutely want to avoid. In fact, this issue is even more complicated. So let's talk about frame rate independence. All that this really means is that you cannot control where your game is run. It could be run on a fast computer with 5000 frames per second, or it could be run on a slow one, where you barely get 30. And as you have seen, even on the same computer, the frame rate can change quite a bit. Meaning we want to make sure that our movement is independent of the frame rate, which at the moment we are not doing, since we are updating the position on every single frame of the game, and this is a massive problem. Just to illustrate it, let me add a table. On this table, we have 3 columns. We have frames per second, which are either 30, 100, or 1000. So this would be the slow computer, and this would be a really fast computer. On all 3 of them, we have the same movement. We always want to move by 10 pixels per frame. But in practice, this doesn't happen, because the actual movement outcome is what we are getting here, where we multiply the current frame rate with the movement speed. On the slow computer, we will get a movement of 300 pixels per second, while on the fast one, we will get 10,000. Those 2 games would feel wildly different. In practice, it would simply mean that both are unplayable. So this is a really big problem that we have to account for. This you could fix in 2 ways. The easier but suboptimal solution would be to set a fixed frame rate. This you could get via set target FPS, and then set a frame rate of, let's say, 100 frames per second. If I now run the game, the ship is going to move much more slowly, but it is moving consistently because our frames are constant. This would work, but it's not great, because for a good-looking game, you want to have as many frames as possible. Basically, the more frames you have, the smoother and the better your game is going to feel. Also, you cannot guarantee that the computer is always going to hit 100 frames per second. If it dips below that, you are back to the original problem. Which means set target FPS could be a solution in some cases, but most of the time you want to avoid it. Instead, you want to use another solution, and that is called delta time. Delta time is the time it took to render the current frame, or the time difference between the current and the last frame. You see both terms online, they mean the same thing, so don't worry too much about that. If our current frame rate is 60 frames per second, then delta time is 1 second divided by 60, or about 0.0167 seconds. This information is surprisingly useful, because here's the original table, where we have the very inconsistent movement speed. This part here is a massive problem. But we can fix it using delta time, which we can do by adding another 2 columns. Delta time is this column here, where we simply get, for example, for 30 frames per second, 1 second divided by 30, the result is 0.033. If our frame rate is 1000 frames per second, we're doing 1 second divided by 1000, and we're getting 0.001. This information we can then use inside of this final column, where we are getting the proper movement per second. All we're doing in here is we are getting the current frame rate, we are multiplying it by the speed, and then we are multiplying all of this by delta time. The result is going to be the same number regardless of the frame rate, which is exactly what we wanted. And in practice, all that's really happening is that delta time and the frame rate cancel each other out. For example, if you have 1000 and you multiply that with 1 divided by 1000, you are simply left with 1. Which is pretty much all that we wanted. Let's implement that one. For that, first of all, we have to get delta time, which I want to store in another variable, dt. The method we want to call is getFrameTime. And this we want to multiply with our movement speed. Although I guess before we are doing that, let me simply print what we're getting from delta time. If I now run this, we're getting a really low number, 0.000 and then some numbers. That is because our frame rate is somewhere between 2000 and 4000, which is totally fine. You want to have as many frames as possible. The lower delta time, the better. The only reason why we don't have movement in this game is because the movement speed is incredibly slow. If I change this to 100, then we have some movement, and this movement is super consistent. It would also be consistent on different computers. And in practice, this system is quite simple. You basically want to get delta time and then multiply it with any kind of movement change. Once you have that, you have frame rate independence. That's literally it. That would be the foundation of movement. And once you have gotten through the theory, it's actually really simple. All you need is a vector to store the position, delta time, then you get vector x or y, and make sure that you're multiplying this with delta time. After that, you can draw the result, and you're good to go. In practice though, you want to add a few more minor things. You want to have a ship underscore direction, which can also be a vector 2 with a default of 0 and 0, and you want to have a ship underscore speed. Let's set this to 100 once again. Once you have all of that, instead of ship x plus 100 times delta time, I want to get ship position x plus ship direction.x multiplied with ship speed, and then multiply that with delta time. This I want to duplicate, and then ship position y plus equals ship direction multiplied with ship speed and delta time. This at the moment is not going to do anything because we don't have a direction. But once we set direction to a vector of 1 and 0, we are going to the right. If we set this to 1 and 1, we are going to the bottom right, and so on. You can also change the speed to, let's say, 200, and then we would be moving quite a bit faster. Via that system, it becomes much easier to move the ship in pretty much any direction, and you don't have to directly target the ship position. This is making things just a bit more accessible. This isn't something that you have to do, but I think in practice, this is the easiest system to manage movement inside of a game. And to finish up this part, I want you guys to do an exercise. Make the ship bounce around the window. Pause the video now and see how far you get. For this exercise, let's start it again. The ship is moving to the bottom right, and once it hits this bottom corner, we want to reverse the direction, or the ship direction to be a bit more specific. All we need for that, before we are doing the movement updates, I want to check if ship position.y is greater or equal to 1080, which in my case is the height of the window. If that is the case, I want to update the ship direction. More specifically, ship direction.y should be -1. That's basically all we need, although before I'm running all of this, I want to increase the ship speed to 800, just so we don't have to wait for too long. If I now run this again, the ship is bouncing. That means next up, for the right side, I want to check if ship position.x is greater or equal to 1920. Then I want to set the ship direction.x to -1. And I think you get the idea. If the ship is at the top, we want to check if ship position.y is smaller or equal to 0. And if that is the case, we want to move down. So ship direction.y should be 1. And finally, if the ship position.x is smaller or equal to 0, then we want to move to the right, meaning ship direction.x should be 1. With that, I can run all of this again, and the ship is bouncing around the screen. That looks about alright, although there are some minor things that you might want to work on. If I set the movement speed back to 100, and then wait just a bit, you can see it there. The ship moved roughly here. That is because if this is the window, the one we have to find up here, we are always placing the top left of the ship. As a consequence, when we are doing something like this line here, where we are checking if the Y position of the ship is greater or equal to 1080, we are checking if the top left of the ship is at the bottom of the window. But this is only triggered once the ship is already below the window. To fix that properly, you would want to check the size of the ship and then subtract the number from 1080. In my case, I am going to be a bit more crude and simply subtract 40 from Y and 100 from X. Besides that, I want to set the movement speed back to 800, run this again, and now this looks about alright. Not perfect, but good enough. Other than that, at this point, we can move things around inside of our game. In this section, we are going to learn about input. By the end of it, we can move a spaceship around using mouse or keyboard input. And input is one of the easier parts inside of Raylib. You can check keyboard, mouse, gamepad, or touch input, and for each of those, you have a couple of basic methods. That's pretty much it. This part shouldn't be too difficult. All you really have to do is go to the documentation, scroll down inside of the first bit, and somewhere you find input handling functions. There you get the keyboard, gamepads, mouse, and touch input. You can also check for gestures, but all of those get a bit more advanced. I'm going to focus on the keyboard and mouse input. I want to start with mouse input because this one is the simplest one. You could, for example, get the X or the Y position of the mouse, or you could get all of that inside of a vector too. You can also get the mouse delta, which is how much the mouse has moved since the last frame. Besides that, you can check if the mouse buttons have been pressed and if the mouse wheel has been moved. You can also set the mouse position, but that's rarely important. To learn about all of that, I have another Python file called free_input.py. This already contains a couple of basic things. We are doing the normal imports, we are initializing the window, and then we are getting the ship that we have seen in the last part. Although at the moment, this should be 0 and 0, so we don't have any ship direction. After that, we are clearing the background and drawing the ship. The end result is going to look like this. Not much happening at the moment. To fix that, before we are doing the drawing part, I want to check for input. Specifically, I want to look for mouse input. The methods here generally start with get, mouse, and then something something. For example, get mouse position, get mouse wheel move, get mouse X, Y, and so on. I suppose what we could start with is get mouse X. This method doesn't want to have any arguments, it simply returns the X position of the mouse. If I print it and show my mouse, the further I go to the right, the larger this number becomes. On the left side, this number is roughly 0 and 0, although if I go a bit further to the right, they can even become negative. And the more I go to the display width, we're getting very close to 1980, somewhere here. You get the idea. This can be useful, but usually is not what you want, because a much more useful method for the mouse position is get mouse position. Don't forget to call this one. This will return a vector2, which means this we can use right away to override the ship position. Or in other words, I want to get the ship underscore position and set this to wherever the mouse happens to be. With that, if I run this again, the top left of the ship is going to be wherever my mouse is, which is quite a nice effect. And that's basically it to get the mouse position. You can either get X, Y, or both. Other than that, you can check for mouse buttons being pressed. Those you can find under is underscore mouse, and then you have button down, button pressed, button released, and button up. And really quickly to understand the difference between them. You have button down and button up. Those check continuously if the mouse button is either held down or not held down. Besides that, you have button pressed and button released. Those are checking if the button has been pressed or has been released. In practice, the difference between them is that these are running continuously, whereas button pressed and button released are a one-time thing. I believe once I demonstrate all of this, it should become fairly straightforward. Let's start with a really simple one, is mouse button down. For this, we want to have one argument, which is the mouse button we want to check. 0 is the left mouse button, 1 is the right mouse button, and 2 is the middle mouse button. In my case, I want to check the left mouse button and then print the result. Like so. If I now run all of this, we get false by default, but if I click the left mouse button, this becomes true. If I release it, it goes back to false. That's really all that this one is doing. If you change this to a 1, then you're checking the right mouse button, and so on. This effectively gives you the state of the mouse button, which can be useful, but very often is quite problematic. For example, if you want to check if a mouse button has been pressed, for a specific button in the game, for example, you could do if and is mouse button pressed. Let's copy all of this with the left mouse button. If that is the case, I want to print mouse button pressed. This is going to work, but it's not going to work well. If I comment out the earlier line and only check for this if statement, if I run the game now and I press the left mouse button once, we're getting mouse button pressed many, many times, even though I only pressed this button once. What happened here? This game at the moment runs at something like 4000 frames per second, meaning we are checking this if statement 4000 times per second. Even if I press the mouse button for a tenth of a second, this would still be hundreds of times of this while loop. And as a consequence, we are printing this statement multiple times, even though for me as a user, it looks like I only pressed this button once, which really is not ideal. The solution to that is instead of mouse button down, you want to check for mouse button pressed. This one fixes everything. If I run this now and I press the left mouse button, we're getting mouse button pressed only once. And this works multiple times. It's fairly straightforward. Mouse button up and mouse button released are basically the inverse of mouse button down and mouse button pressed. For example, if I add mouse button released, run all of this again, I can click with the left mouse button, nothing happens, but if I release it, we're getting mouse button pressed. That's really all that you're getting from these functions, which I think overall is all you need for mouse input. So next up, we can work on keyboard input. And while we are doing that, I want to comment out all of the mouse input so we're not getting confused. All of this should be commented out. For keyboard input inside of the documentation, you only have a couple of functions. Like for mouse input, you are separating between pressed and down. Meaning for is key down, you are checking continuously if a button is currently pressed or not. Whereas for key pressed, you're only checking this once. Like it says in the documentation, once and again here is super important. The only difficulty for this one is that you want to be aware what kind of key you are looking for. For which you have a whole bunch of constants, it's honestly not that difficult. Back inside of the code, I want to print the result of is key down, pressed, pressed repeat, released, or up. For now, I want to go with is key down. As an argument, we want to have an integer, although this integer we're getting from a bunch of constants. The way you access them is if you press key, all in uppercase letters, then you get all of the options available. Simply look for what is available. I want to go with key A. If I now run the game, I get false by default, but if I press A, we're getting true. And this works pretty well. And just like with the mouse, this is key down does not work well with if statements. If I copy it and then do if is key down and then print A. Also, I want to comment out this original print statement. I can now press A once and we're getting an A output multiple times. Once again, to fix that, you do not want to check is key down, but rather is key pressed. If I do that, I can press A and we're getting A only once. Perfect. And well, that is pretty much all you need for basic keyboard input. Obviously, this does get a bit more involved if you have a gamepad or touch input, but those get more advanced, so I'm not going to worry about them. Instead, I want to do an exercise. I want you to move the ship around using keyboard input, specifically the arrow keys. Meaning, if you click right on the keyboard, the ship should move right as well. Pause the video now and work on that one. Back inside of the code, I want to comment out what we have done so far, and then add another section for ship input. To get the ship movement, I want to get the ship direction. This you could target in a couple of different ways. For example, you could check if is key down with key underscore right. If that is the case, I want to get the ship direction.x and set it to a 1. This at the moment is not going to do anything because we are not using the direction. But that we can change quite easily via another part, update. In there, I want to get delta time first of all, which we get with get frame time. After that, I want to get the ship position.x and add ship direction.x multiplied with ship speed multiplied with delta time. The same thing I want to do for ship position y, ship direction y, and keep the speed and delta time. With that, since I now via the input set direction.x, the ship should start moving to the right once I press the right arrow button. Let's try. And if I press right, the ship moves to the right. The problem is, if I release the button early, the ship never stops moving in this direction. Which you could fix by adding an else statement. If this key is not being pressed, ship direction.x should be 0. That way, I can move to the right whenever I want, and the ship also stops once I stop pressing the button. That's a good start, but this isn't really elegant. We have 4 lines of code for something that is really, really basic. A much more elegant approach would be to get the ship direction.x right away, and then check for is key down right, and convert this into an integer. That would do the same thing we have done so far. If I run this now, I can move the ship to the right simply by pressing the button. From this Boolean value, we're getting either true or false, which we are then converting to a 1 or a 0 using the int function. In this system, you can make even more elegant by subtracting the integer of, let me copy all of this, the integer of key left. If I run this now, I can move left and right pretty easily. Let me do an example to illustrate how this works. If we are pressing key right, meaning this is true, and we are not pressing key left, so this would be false. Because of the int function, this would become a 1, and this would become a 0. And 1 minus 0 is going to be 1, meaning we are moving to the right. If we are only pressing the key left button, meaning this one is true and key right is false, then we would be doing 0 minus 1. The end result would be a negative 1, meaning we are moving to the left. If both or neither is pressed, then the end result is going to be 0, so we have no movement whatsoever. This we can do on the horizontal and on the vertical axis. Simply by copying it, and then for the vertical axis, I want to get ship direction Y, and then key down minus key up. If I run this now, I can move the ship around the screen in any direction. That works really well. There's only one final thing that I want to work on. If I move the ship in only one axis, let's say left or right, or up or down, then we have one speed. But if I go diagonally, meaning I go both to the right and down, then the ship starts to move much faster, which I think is fairly noticeable. The issue we have is that this direction doesn't have one consistent length, which is a problem because we are multiplying all of that to get the final speed. Or in other words, if we are only moving to the right, then the vector has a length of 1. Also, if we only move down, then the vector also has a length of 1 only, meaning those two lines in isolation work totally fine. The problem starts to happen when we are going in both directions, meaning we are going 1 unit to the right and 1 unit down. If we do both of those, the length of this vector is not going to be 1. It's going to be 1.4. And this value we are then multiplying with the speed and delta time, which is then giving us a 40% greater speed, which we really don't want since the speed should be consistent. To fix that, we have to normalize the vector, meaning we are setting the length of the vector always to 1, which we already do if we only move on the horizontal or the vertical axis. But if we move diagonally, then the vector should only move by roughly this amount to the right and this amount on the vertical axis. That way, the full length of the vector is going to be 1.0 instead of 1.4. The math for that can get a bit more complex, but we don't have to worry about it. All we need is assign a new vector to ship direction, and the value we want is vector to normalize with one argument, the vector that we want to normalize, ship direction. That way, the full length of the vector is always going to be 1. That way, no matter what direction I am moving in, we always have the same speed, which feels much nicer. That means we are nearly done with input. Just one more thing, and that is you can set an exit key. I usually do that right below initializing the window. For that, you want to set an exit key. In my case, I want to go with key escape, which I think makes the most sense. All that this really does is it toggles window should close to go from false to true. Since we are doing the inverse via not, this should close the entire while loop. And as a consequence, the game is going to end. Let's try. I can run the game, press escape, and the game ends. That looks pretty good. Let's talk about collisions, which in the most basic sense are fairly simple. Basically what you do is check for collisions between a variety of shapes. If you look at the documentation, you have all of these methods. They always start with check collision, and then you can check, for example, for collision between circles or between rectangles or points and so on. I will demonstrate how that works in just a second. But first of all, a very important point is that you are just checking if a collision happened. You are not resolving this collision, meaning there's no position change if there is an overlap. For those proper collisions, you will need a bit more logic. I will cover that later. For now, I want to work inside of a new Python file called for_collisions.py. In there, we are doing the usual. We have a couple of imports, we are creating a window, and then we have the drawing loop. What we are drawing are a player and an obstacle, which are both circles at the moment. As you can see down here, we have draw circle V, for which we have a position and a radius. Besides that, we have a color. The player is white, the obstacle is red. Finally, the player position is going to be set by the mouse position, which we're doing here. The end result is going to be, if I run all of this, we have a white circle following the mouse, and then we have a red circle here. Between those two objects, I want to check the collision. For that, I want to add another section. Let's call it collision. And the end result, I want to print. For that, I want to check _collision. And then we have all of the options. The simplest one, I think, is check collision circles, which wants to have 4 arguments: the center and radius of the first circle, and then the center and radius of the second circle. In my case, I have the player _position and the player _radius. That's the first circle, and the second circle is going to be the obstacle position and the obstacle radius. If I now run all of this again, by default, we're getting false because there's no collision between the circles. Once they do collide, we're getting true. And that is pretty much it. Now we can check if there's a collision or not. Once again, for more detail, you want to look at the documentation, scroll down. The collisions are inside of the shapes part, down here. The method I have just used is check collision circles. But, well, none of those get that much more complicated. That being said, there's one new object that we have to learn about: rectangles. Rectangles in Raylib are a specific object, and shockingly, they are a rectangle, where you define the top left position via X and Y, and then you set a width and a height. From that, you get a rectangular shape, which is surprisingly useful. The 2 most common functionalities are: number 1, you can use it for collision checks, and number 2, you can draw this rectangle. And by drawing, I mean you could either draw the rectangle itself, or you could draw a specific area of a texture, whatever you define via the rectangle. In our case, I want to create, let's call it R1. This we create via rectangle, and then we want to have a position and a size. For now, I want to have 0 and 0 for X and Y, meaning we are on the top left, and then add 100 and 200. This rectangle will be 100 pixels wide and 200 pixels tall. To see it, we have to draw the entire thing, and that we do inside of drawing. I want to have draw rectangle, and then you want to have draw rectangle rec. That way we are using a rectangle object for the actual drawing. If you simply use draw rectangle, Raylib wants to have position X, Y, width, and height as separate integers, which I don't care about. I want to have draw rectangle rec, in which I add R1 for the rectangle, and then a color. Let's go with blue. And now, in the top left, we have a rectangle that at the moment doesn't do very much. That's totally fine though. What we could be doing at this point is comment out the current collision check and then print another collision check. I want to check collision between a circle and a rectangle. For that, we need to have a center and a radius for the circle and a rectangle for the, well, rectangle. In my case, I want to have the player _position and the player radius for the circle and R1 for the rectangle. If I run this again, I have false by default, but if the circle and the rectangle collide, we're getting true. That's really all there is to it. Finally, another thing that we could be doing is define another rectangle. Let's call it R2 by creating a rectangle somewhere on the screen. Let's go with 800 and 500 and a size of 200 by 300. This rectangle I want to draw. Inside of drawing, I want to duplicate draw rectangle rec, draw R2 with the color. I guess we haven't used green yet. And also this should be R2, not R1. If I run this now, we have a green rectangle. And I want to check the collision between R1 and R2. For that to work though, we have to move the first rectangle, which we can do by getting r1.x and set it to get mouse x. The same thing I want to do for y, so r1.y is going to be get mouse y. With that, I am moving the circle and the rectangle. Although the circle I don't care about at the moment, so I don't want to draw this part. Let's try it again, and now we have a moving rectangle and a static rectangle. To get the collision between those two, I want to print check collision between rectangles, for which I only need two rectangles, in my case R1 and R2. Once again, we get false, and if there's a collision, we get true. That's pretty much it for collisions. As I said before, in the most basic sense, these are super simple. They only become complicated once you want to resolve the collision, so that rectangle 1 stops moving once it collides with rectangle 2. This I will cover later. For now though, I want to do an exercise. I want you to get the overlapping rectangle once a collision happened. You can find the function for that inside of the documentation. Once you have that rectangle, draw it. Should be fairly straightforward. Pause the video now and see how far you get. Once again, inside of the documentation, I want to look for get collision rectangle. This will give me the actual overlapping area. As an argument, I only need two rectangles, which means back inside of the code, I want to create a new rectangle. Let's call it the overlap underscore rectangle, which I get via get collision rectangle. As an argument, I want to have R1 and R2. After we have that, inside of the drawing bit, I want to check if the overlap rectangle exists in the first place. If it does, I want to draw it, which I'm doing via draw rectangle rec, where we are drawing the overlap rectangle in a certain color. Let's go with red. I can now run out of this again. I can move the rectangle around, and once we have a collision, I'm getting the overlapping rectangle. That works really well and is a super cool effect. Unfortunately, this only works with rectangles. If you had a circle or some kind of line, you would have to create your own logic. That would be possible, but quite a bit of work. In practice, most collisions happen via a rectangle, simply because those are the easiest one to work with. A really important part of any video game is a camera. That way you can explore a level and see the actual world. Implementing all of that in Raylib is quite easy, since you have dedicated camera functionalities. This also allows you to rotate and zoom and is ultimately fairly powerful. And to explore the camera, I have a new Python file called 5camera.py. In there, we are already doing quite a few things. Let's go over it really quickly. We are importing Raylib, and then we are using the random module to get randint and choice. Those we are using down here to create a whole bunch of random circles. I'll talk about this in just a second. First of all though, we are creating a basic window and we are setting up some attributes for the player. I think one part I haven't talked about yet is that if you create a vector2 without any arguments, you're getting 0 and 0. This player is going to move around on the screen. For that, we have the usual stuff. We are getting player input and normalize the vector. After that, we are using that information to move the player around. All of that gets drawn down here. That way, for the player, we're getting a black circle. That's the part that should be super easy. Besides that, we are doing all of this. What's happening here? This is a list comprehension in which we are creating this tuple for I in range 100, meaning we are creating 100 tuples. For each tuple, we're getting 3 bits of information. A vector2 for the position, and for x and y, we are getting random values that are between -2000 and 2000 for x, and -1000 and +1000 for y. Next up, we have a random integer that is also a random value between 50 and 200. And finally, we are picking one of these colors. By the end of it, we are going to get a list with 100 tuples where each tuple contains these 3 bits of information. All of that we are using a bit further down on these 2 lines, where we go through every single circle, and then we are calling draw circle v, where we are unpacking the circle, which is going to give us the vector 2 for the position, the random integer for the radius, and then the color for the, color. The end result is going to look like this, where we have a whole bunch of circles and the player can move around. That is looking okay, but now we have a problem. The circles extend for quite a while. For example, we have a whole bunch of random circles here, 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 and I think you get the idea. Outside of this screen, we have a whole bunch of circles that we cannot see yet. To see those, we need a camera system. This consists of 2 parts. Number 1, we have to create a camera itself. This I want to store in a camera variable. To create it, you want to type camera 2D. No need for any arguments. After you have that, when you are drawing everything inside of this part, you have to add begin mode 2D. And as an argument, you add the camera that we have just created. So camera in there. Also, after you finish drawing the camera part, you want to end mode 2D. Although this one doesn't need any arguments. If you're doing that, all of this stuff will be relative to the camera. Although if you're running this now, nothing is going to happen. So this is not ideal yet. The issue we have at the moment is that this camera needs just a bit more setup. The most important part for now is that we need to set the camera zoom, which by default is 0, which is going to break everything. A much better value for this one would be 1, which is going to get you back to the default view. So this is feeling much better. At least we can see something, but the camera still doesn't do anything. That is because the camera needs a target, which should be a vector 2. Specifically, we should get the player position, which means I want to have the position of the player in there. And now this still doesn't do anything. That is because this target needs to be updated continuously, which happens inside of the while loop. I want to add another section for the camera update. In there, I basically want to copy this line. Camera target is the position. If I now run all of this again, I can move around, and we are moving the entire screen. Although the player is always in the top left. That's not ideal yet, but at least we're making progress. To get the player in the center of the screen, you want to give the camera an offset. The value should be a vector 2, and then we need an x and a y value. By default, we're getting 0 and 0, which puts the player in the top left. But if I change this to, for example, 500, run this again, now we're moving the camera 500 pixels to the left effectively. We can do the same thing on the y-axis. If I set this to, let's say, 1000, then we have moved up the camera relative to the player by quite a few pixels. And to get the player right in the middle, you want to get the window dimensions, which in my case are 1920 by 1080. I want to get half of that, meaning 1920 divided by 2 and 1080 divided by 2. And let me add a bit of white space so this looks better. If I now run this again, we have the player right in the middle, and we can move around and explore the level, which looks really nice. That would be the most basic camera setup, where you want to get a camera setup and then update this camera. On top of that, you have to include begin mode 2D with the camera and then end mode 2D. Anything that is not between these 2 lines will not be affected by the camera. So just keep that in mind. What you can also do with the camera is set a rotation and a zoom level. If I set camera.rotation, for example, to 20, then, well, this is quite hard to see. But if I now simply move up, we are moving at an angle. If I make this a bit stronger, let's say 45, run this again, I am only going to move the player up. I am pressing nothing else besides the up button. But if I move in this way, we are moving at an angle. That is because we have rotated the camera, which is very hard to see if you only have circles. Maybe not ideal, but if we update this in real time, it's going to be visible. For that, the default camera rotation should be 0, and this we want to update inside of the game. For that, first of all, we will need let's call it a rotate direction. This is going to work similar to what we have done with the movement input. In fact, let me copy it. I just need different keys. Let's say for this one, I want to get key S minus key A. That way we are checking the S and the A key on the keyboard. And those I want to use to update camera.rotation. I simply want to add plus equal rotate direction multiplied with delta time and multiplied with some other value, let's say 50. So the rotation isn't too slow. If I now run all of this again and I press S and A, we are rotating the entire world, which can be slightly nauseating, so I hope it's not too confusing. And to zoom the camera, you could use a similar system, although that part is going to be your exercise. I want you to zoom in and out using the Q and W key on the keyboard. You could use any other key, it doesn't really matter. I just want you to have some kind of functionality so you can zoom in and out. Also add a system so the camera doesn't break if you zoom out too much. You'll see what I mean if you experiment just a bit. Anyway, pause the video now and see how far you get. We have already seen that camera zoom is the, zoom. This we want to control, for which we first of all need, let's call it a zoom direction. For that, I want to once again copy what we have done up here, and then change this to key W and key Q. Once we have that, I simply want to get camera.zoom and add the zoom direction multiplied with delta time, and then I multiplied all of this with 2, so it's a bit snappier. If I now run all of this, I can zoom in and out, I can zoom in quite a bit, and I can zoom out a lot as well. Although if you zoom out too far, let me try to get it, then we are inverting the entire thing. Right now I'm pressing up, but the player is moving down. That is because the camera got really confused. If I zoom out once again, the camera works just as intended. If these values become too large, you are going to get some really weird behavior. To fix that, you want to get camera zoom once again, and then assign a limiter to it, which you do by first assigning a max value, meaning we are picking the larger of 2 values. I want to go with 0.2, and then the camera dot zoom. If I now run this again and I zoom out, then we can never go beyond this point. We can still go back, but this is pretty much what we need. And by the way, the issue we had earlier, where the camera inverted, is where we reached a value below 0. If you wanted to have another limiter, you could add min here and then set something like, let's say 5. That way, we can only zoom in up to a certain level, meaning if I run this again and I zoom in, we are stopping somewhere here. Let's go with something smaller. Let's go with 2. And now I can zoom in only up to this point. And I can still zoom out quite a bit, but this feels a bit nicer. For this system, simply play around and see what looks best for your game. There isn't really a universal answer. The last major part for the absolute basics of Raylib is going to be music. So we can play audio files. For that, if you look at the documentation, you can go down for quite a bit. At some point, you will find R audio. This gives you all of the methods that you are ever going to need. The really important stuff here is, first of all, you have to set up the audio device. It can be a bit annoying, but you have to deliberately activate audio playback. After that, you can load and play a sound file and load and play a music or an audio stream file. And that's pretty much it. Which I think already begs the question, what's the difference between sound and music? Sound files are stored in the RAM and should only be used for effects. That way we don't clutter up the RAM too much. Music, on the other hand, is streamed from your hard drive, which makes them a bit easier to work with from the resource perspective. So especially for background music and longer tracks, this is what you want to do. And that's basically all you have to do for the differences. If you want to have effects, you want to have audio files. If you want to have background music, you want, well, music. Inside of VS Code, I am working inside of 6_audio.py. Besides that, if you look at assets, we have laser and music.wav. Those are the two files I want to work with. Although first of all, for that, we have to set up audio playback, which in practice means below init window, you want to init an audio device. Don't forget to call this one. After you have that, you can play audio files. Although what you also want to do, after you have finished the game, you want to close the audio device. Once you have all of that, you can load and play an audio file. For example, in my case, I want to have a laser sound, which we are getting via load_sound with a path that we're getting from join. I want to go to assets, and in there we have laser.wav. To play this file, all we have to do is play_sound with the laser sound. If I now run the code, we are getting a laser sound. Besides that, if you want to play music, you want to load a music stream, for which, once again, you will need a file path. I want to get to assets, and in there we have music.wav, this file. To play that, we will need a couple of things. First of all, we have to call play music stream with the audio file we have imported. For that, I want to create a music variable and paste that one in there, music. If I run this now, we're getting the laser, but not the music. For that, we have to update this music stream, which happens inside of the while loop. You want to call update music stream with the music file, the one we have imported. Finally, at the end, you want to unload this music file as well, which you're doing with unload music stream. And once again, the music file you have imported. Once you have that, you are getting music. And that is pretty much it for audio. You can either play a single sound effect. For that, you want to have a sound file, or you can play background music that is streamed directly from the hard drive, for which you want to have a music stream. Which means we are done for this part. Music is usually quite easy. At this point, we have all of the basics of Raylib, at least for 2D, meaning we can create pretty much any two-dimensional game. That being said, to create complex games, you want to have one more really important ingredient, and that is organization. If you want to create more complex games, you want to use classes. That makes it much easier to manage larger projects. Especially for a game with multiple entities, for example, a player and a couple of lasers, this becomes incredibly important. So let's talk about it. When we are talking about classes, we basically talk about that we want to use object-oriented programming to organize our game. For example, a spaceship class might contain the texture, position, and movement for that spaceship. On top of that, via inheritance, the entire system can become even more powerful. For all of that, I have a new Python file called 7classes.py, which at the moment really doesn't do very much. We have basically the minimal setup for Raylib. If I run all of this, we're getting a black screen, which is totally fine. On this screen, I want to move the player around. And for that, I want to create a class called player. In there, I want to call it under init method, which will need self and let's say a starting position. This we then want to store inside of the class, so self.position is going to be the position. On top of that, I want to get self.texture, which we have to import, which happens via load_texture. And then via the join method, I want to go to assets and then get, I think it was called spaceship.png. we want to go to assets, and in there we have spaceship.png, the file we have already seen. Simply with that, we can already create one instance of the player. So player is going to be player in one position. Let's say 500 and 200. This should be a tuple as well. To draw all of this, I want to call draw texture v, where we get player.texture and player.position. The tint color, as always, is going to be white. And now we have the ship somewhere on the window. This works really well. And very importantly now, we have all of the player attributes in one place, the class, which makes it much more organized. And this is just the start. This system can become even more powerful. For example, what we could be doing is organize the drawing of the player inside of the class itself. I guess we could call this the draw method, which will always need self. But other than that, we simply want to call draw texture v, the line we have already covered down here, and add it in there. The only change we have to make is instead of player, we want to have self. That way, we can simply call player.draw, and we're getting the same result, which does feel a lot more elegant. Now we have all of the logic contained inside of the player. Another nice thing that we could be doing for this is define an update method that we call continuously. In there, for example, we could move the player, for which I want to go back to input and copy all of this stuff. Paste it in here, and then we have to make a few minor updates. First of all, we want to get a direction for the ship, which we define inside of the init method. Self.direction is going to be a vector2. This self.direction we are then updating inside of the update method. So instead of ship direction, we want to have self.direction. After that, I want to update the position of the ship. Or in other words, I want to update self.position. The direction is going to be self.direction, and then we need self.speed as well, which doesn't exist yet, but is super easy to get. Self.speed is going to be, let's say, 400. With that, we are updating the position of the ship and then draw the entire thing down here. As a consequence, all we have to do inside of the game loop is simply call player.update, and then we are getting an error. And that is because self.position.x doesn't exist. That happened because the position at the moment is a tuple, not a vector2. This should be a vector2 with that starting position. Now this should be working, and we can move the player around just fine. This is really nice. And well, with that, we have a fairly powerful player class that we could minimize and then not worry about it again. Inside of the actual game logic, this is barely visible. Meaning, if you have multiple classes and lots of stuff going on, this kind of system makes your game much more manageable. Which is why it's something you basically always want to do. To practice all of that, I want you to create a block class that slowly moves to the right. Also, while creating this class, you should be able to set the speed and the position of this block. And by position, I mean starting position. The other things like color and size, you can set on your own. It doesn't really matter. Pause the video now and see how far you get. I want to create another class called block, for which we will need a dunder init method with self, a starting position, and the speed. This we then want to store inside of the class, meaning self.position is position and self.speed is going to be the speed. On top of that, I want to have self.direction, although this is always going to be a vector2 that points at 1 and 0, meaning we're going to the right. Once we have that, to actually see something, I want to get a draw method once again with self, in which I want to draw a rectangle V, for which we need a position, a size, and a color. The position we already have. This is simply self.position. Then we need a size. For that, I want to have self.size, another vector 2 with, let's say, 100 pixels for the width and 200 pixels for the height. This is going to be self.size. And finally, we need a color. This could simply be red. Doesn't really matter. With that, we should already be able to see something. Although, first of all, we have to create one instance of the block, which we do by calling the block class, and then give it a vector 2 for the position, let's say 700 and 0. And we need a speed. This should be an integer, 200. After that, below the player, I want to block.draw. Let's try this now. And we are getting a block that doesn't do anything at the moment, but at the very least, we can see something. To move it, we want to call define update once again, and then basically do what we have done up here. I can literally just copy it. I guess we don't need the comment. And now I just have to make sure that before we are drawing the block, I want to call block.update. So now this block is moving to the right. That looks really good. Perfect. And well, that's the basic idea of using classes to organize your game better. That being said, we are not done yet. Because if you look at these two classes, we have lots of things that we are repeating. Most importantly, these lines here are simply copy-pasted, which is not a good practice. To make this even better, you want to have a parent class that contains these methods, and then you don't have to copy them. Which means I want to create a class called sprite. A sprite is basically just a 2D object. It's a fairly generic class. For this, I want to have a dunder init method, for which we are getting self, position, and speed. Both of those we are simply storing as attributes, meaning self.pos is pos, and self.speed is going to be speed. Once we have that, we can already update the classes. For the player, I want to inherit from the sprite class, which means when we are calling this dunder init method, we also have to call super dunder init to initialize the parent class, which needs a position and the speed. Position we are getting from the parameters. That one's fine, but we don't have speed. Now for the player, speed is simply going to be 400, the one we have defined earlier down here. Also, since we now define self.position inside of the sprite class, we don't need it inside of the player anymore. This one can simply go. If I now run all of this again, it should still work, and it does. That looks pretty good. Cool. Besides that, inside of the parent sprite class, I want to define a move method, which needs self and delta time, which is going to do all of this. Although we only want these two lines, let me cut them out and paste them in there and then fix the indentation. Inside of the player class, all that we really want to do is call move with delta time. Or, well, self.move. Now, self.move we can get from the parent class, but we cannot get delta time. This I want to get via the parameter. Inside of update, there should be delta time. And then, inside of the game loop, I want to get, before we are doing anything, delta time via get frame time. And then pass delta time inside of the player update method. In fact, play update shouldn't even be inside of the drawing loop, it could come before. Since play update doesn't draw anything, it shouldn't be inside of the drawing bits. And now, when we are calling this update method, we are getting delta time and pass it into the move method that is inside of the parent. Inside of this parent move method, we are updating the position via direction, speed, and delta time, all of which we have inside of the class. Which means now everything should still work just as before. That's looking pretty good. Cool. That covers the player. Next up, we can also update the block, which first of all should inherit from the sprite class. Which means for dunder init, we want to call super dunder init, which wants to have a position and a speed. both of which we're getting from the parameters. As a consequence, we don't need either of these lines anymore. Besides that, for the update method, I first of all want to get delta time via the parameter, and then I can replace all of these lines with self.move and delta time. Once again, the method we have defined up here. That is nearly it. The last thing that we have to do when we are calling block update, we have to add delta time in there. And this line, like for the player update, should be before the drawing part. If I now run this again, we have once again the same result. Looks pretty good. And I hope you see the value of this kind of system. Via that, we have a sprite class that contains all of the really important parts. And then, for the player, we are basically just adding a texture and an input method, and then we are moving all of this. For the block, we are not really doing that much more. We are still having the sprite class, but then we are setting a direction and a size, and other than that, we are simply moving the thing and drawing it. If you have lots of objects on the screen, this is going to become really, really helpful, because you only ever work with one object. The last thing that I want to cover is that we are calling the same method multiple times. So we're calling update twice and draw twice. This could be a bit more elegant. For example, what we could do is create a sprites list, which is simply going to contain the player and the block. Like so. Then we don't need player or block variables anymore. Instead, when we are updating things, I want to get for sprite in sprites, and then sprites.update with delta time. That way we can get rid of these two lines and copy all of this for the drawing part, in which we want to call, this should be sprite.draw and sprite.update. The end result, once again, is going to be the same. But now you could have thousands of sprites. They would all be updated simultaneously. So once again, once you start working with multiple objects, this kind of system is going to be much more robust. But as always for beginners, classes and inheritance can get a bit more confusing. So I hope this part wasn't too bad. Ideally, go over it in your own time and practice this system a lot. For more complex games, it's really, really important. We have already seen the system to check if two objects are colliding with each other, which is a good start, but doesn't really feel satisfying, because effectively we are simply checking for overlaps, not for collisions. This we're going to fix in this video, where we are going to cover collision resolutions, meaning that objects actually collide and we are updating the position. For those actual collisions, the most important thing is that objects cannot overlap with each other anymore, which effectively means that we first detect an overlap and then we update the position of the objects. For that, we have to implement a collision system, which consists of three parts. Number one, we separate the dimensions, meaning we first look at the horizontal axis and then the vertical one, or the other way around. The order doesn't really matter. After we have that, we check the direction of the moving object, i.e., if we're going left or right, and this will determine where the collision happened. For example, if we are currently on the horizontal axis and we have one moving object, that is the player. Besides that, we have some kind of obstacle that we are currently overlapping with. We know there's an overlap. This is easy to detect. The issue we have is that we don't know by default which side we are on. Are we on this side or on this side of the obstacle? It's really tempting here to assume, since the player is on this position, that the collision happened on this side. But that's not necessarily the case. What could have happened is that the player on the last frame was somewhere here and simply moved super fast, so that we ended on this position. So what we are going to do is check the movement direction of the player. Meaning, if the player has been moving to the right and we have an overlap, then we know the collision really happened here. If, however, the player moved to the left, then the collision must have happened on the other side. The advantage of this system is that it's really easy to implement. The downside, however, is that it only works with a single moving object. Once we have two moving objects, it falls apart pretty badly. If you want to learn more about that, check out my Pygame tutorial, which is much longer and covers different kinds of collision behavior. In there, I cover collision between moving objects and also something like platformers. Anyway, once we have all of that, we want to update the position to have an actual collision. For all of that, I have a new Python file called 8collision-resolution, which once again contains quite a few lines of code. So let's go over it really quickly. As always, we do the imports and then we set up the window. That part should be easy. The next easy part is the player with a speed and direction, which we are using a bit further down. To update the direction via user input, then we get the movement, and all of this we are drawing down here. The player is basically a rectangle that is being moved around. That part should be really simple. The more complicated part is all of this and this. We have a level map, which is a list that contains individual strings. Inside of the string, we have ones and zeros. Wherever we have a 1, I want to place a block, and if we have a 0, I want to do, well, nothing. The logic for that is this for loop down here, where we first of all go through every single row, which effectively is each string. And via enumerate, we know that we are, for example, on row 0, 1, 2, 3, 4, and so on. After that, we have an inner for loop, which goes over each individual row. Once again, we are using enumerate to know where we are. The first entry would be 0, then we have 1, 2, 3, 4, and so on. That information we can then use for the actual position, where we are getting the column index and the block size. For example, if we are down here on the first item, column index would be 0 and the block size would be 100. Effectively, x would be 0. If, however, we are on the second one, this one here, this value would become a 1. So x would be 100. This continues until we reach the end of the line, and that way we're getting an x and a y position for each block. On top of that, since we are creating a rectangle afterwards, we have the block size, which we have to find up here. After that, we are appending the block to the blocks list, and then inside of the drawing part, we are going through every single block and drawing them. By the end of it, we have a whole bunch of rectangles where we can move the player around. At the moment, there are no collisions, which is totally fine. For that, all the way at the top, I want to create a collision function, for which we want to get one argument, the axis. So we have to create an axis parameter. First of all, in there, I want to go through every single block, meaning for block in blocks. After that, I want to check if there's a collision in general, which we can do with if check collision underscore rex, in which we are checking a collision between the current block and the player, both of which are rectangles. If that is the case, we know we have a collision. Let's print to see if that works. We want to print collision. We have to make sure that we are calling all of this, which I want to do right below the movement, collision, with one argument. For now, it doesn't really matter. Let's say x for now. If I run this now, I can run around, and if I have a collision, we're getting collision. So we know when we collide. That's a good start. The problem now is that we don't know where the collision happened. For that, we have to cover the first part, where we separate the axes. In other words, I want to check if axis is equal to x, then I want to do something. For now, let's say pass. And if that is not the case, else, I want to do something else. Also pass for now. And then, inside of the player movement. After we have done the horizontal movement, I want to check for the horizontal collisions. Next up, I want to do the vertical movement and then check the vertical collision, meaning collisions y. That means when we are moving on the horizontal axis, we are only checking this part. I want to check if direction.x is greater than 0, meaning we are moving right. So at this point, we know that we have a collision and we know that the player is moving to the right. And since the player is the only object that is moving, we know that the collision must have happened on the right of the player. As a consequence, we want to update the player X position to block.x minus the player.width. Let's try this one. If I only move to the right and I have a collision there, the player stops. That is actually working. Although if I do anything else, we are getting some super weird behavior. But let's talk about this line really quickly. At the moment, we are only on the horizontal axis, meaning we can only go left or right. On there, we have the player and we have an obstacle. We know of those two colliding because of this line here. If that one triggers, we know that we have, for example, something like so. Once again, we know there's an overlap, so there must have been some kind of collision. We just don't know on which side of the obstacle it happened. It could have happened here or here. To figure this one out, we are checking the movement direction of the player, which at the moment is going to move to the right. As a consequence, the collision must have happened here. Once we know that, we want to update the player X position, which is going to be this part. We want to set the player X, that's the top left of the player. And this we want to move roughly here, which is going to be to the left of the block, and the distance is going to be the player width. That way, the player will be exactly on the left side of the obstacle. And with that, we have collisions on one side. To get the other side, I want to check if direction.x is smaller than 0, meaning we are moving left. And if that happens to be, I want to update player.x and set it to block.x plus block.width. Let's try if this one is working. I only want to move to the left, and we're getting a collision. That looks pretty good, although once again, if I do anything else, we are teleporting. Once again, to understand this line, we can only move left or right at the moment. For the left collision, we have a player here, and we have an obstacle roughly here. Since the player is moving to the left, we know the collision must have happened here. As a consequence, we are updating the player position so that the player is exactly on the right side of the obstacle, which means we want to get the top left of the obstacle and then move along the width of this obstacle. After which we are placing the top left of the player, which is then going to be exactly on the right side of this block. That covers the horizontal collisions. A similar thing we have to do for the vertical ones. This is going to be your exercise. I want you to implement the vertical collisions. For that, you can copy a lot of ideas from the horizontal collision logic. Pause the video now and see how far you get. I want to check if direction.y is, let's say, smaller than 0. If that's the case, we are moving up, which means I want to update player.y to block.y plus block.height. Let's try this one, and if I move up, at some point the player stops. That looks pretty good. Perfect. Besides that, I want to check if direction.y is greater than 0, which means we are moving down. Then I want to update player.y once again and set it to block.y minus player.height. And that should be all we need. If I now run around, let's check the bottom collision. This one works. And besides that, since we now have all the 4 sides, I can collide pretty well with literally anything. The player will always be stopped, and this gives us proper collisions. Next up, we're going to work on timers. Those come up in video games surprisingly often. And this is also the part where Raylib doesn't really have that many pre-made tools. If, for example, you want to have a repeating timer, you would have to create custom logic. Raylib only gives you the very basic tools that you need to measure time. For anything else, you have to make custom solutions. What we are going to do in this video is create a timer class that can run for a certain amount of time, can run repeatedly, can auto start, and can trigger a function once it times out. Although to be a bit more specific, I will only talk about how to use the class. The actual logic I have covered in another video on Pygame. Check this one out if you want a bit more detail. the logic is going to be identical compared to what we are doing in Raylib. Here we are back in VS Code, and I am working in 9timer.py, in which we have a couple of lines of code, 50 in total. We are doing the basic Windows setup, and then we have two classes. The first one is a basic sprite that doesn't do all that much. We are initializing a rectangle and a color. Via the parameters, we can set a position and a size. All of this gets drawn, and we have one method to randomize the color, which simply updates the color parameter, which we are then using for the drawing bit. Besides that, we have a timer class that is a good bit longer. So let's go through it slowly. And once again, if you want to create this thing from scratch, check out this other video. There's only one line that changes, and that is this one here to get the current time. In fact, let's talk about it. Inside of Raylib, you have a method called getTime. This will give you the time since you have called init window, this line here. Or in other words, if I print get underscore time, we are going to get the time in seconds since we have called init window. If you call this multiple times inside of the while loop, this number is going to increase. Here you can see we are basically measuring the time since the start of the game in seconds. Not terribly complicated. That is also the main way to work with time inside of Raylib. Or in other words, if you look at the documentation inside of the core module, you can go down a bit, and somewhere in there you have timing related functions in which you can set a target frame rate, you can get the current frame rate, you can get the current time, and you can get the current FPS. That's pretty much all you get for time inside of Raylib. It's not very much. Meaning if you want to have a repeated timer, for example, you would have to create your own logic, which is what we're doing with this timer class. So let's go through it. First of all, we are initializing the entire thing and set up a duration, a start time, if the timer is active, if it's repeated, if there's a function, and if we should auto start. The way you're using them is first of all by activating the timer with activate. This one sets active to true, and then we're getting the current time. This will be the start time. After we have done that, we are calling the update method, which contains the main part of the logic. This first of all checks if the timer is active. If that's the case, we are doing this line, which is the main part of the timer, in which we are checking the current time, so how much time has passed since we called init window, and from that, we are subtracting the start time. Or in other words, if you have a timeline, with the start point being 0, or whenever we have called init. Once again, this line down here. From this point, we keep on measuring the current time. Once we have that, to create a timer, all we need is to measure a point in time once, which is what we are doing with the start time. And from that, we want to measure how much time has elapsed. If this elapsed time is longer than some duration, then we know the timer should trigger. And this is what we are doing down here, where we get the current time, which we are comparing against a start time. And if that value is greater than a duration, the timer has triggered. If that is the case, we want to do something. If there's a function, we want to call that function, and then we want to deactivate the timer, which happens here. All we're doing in there is set active back to false, start time to 0, and if the timer repeats, we are going back to activate. And that way, we have a timer. That's really all that's happening in here. Fundamentally, it's not a complicated concept, or at least I hope it isn't. So let's use it. For that, you want to create a timer variable and then assign one instance of the timer. The one argument you always need is a duration, and this one is in seconds. Let's say for now, I want to have a timer that runs for 1 second. After that, you get a whole bunch of arguments that have default values, which means you could ignore them. But in my case, I want to set repeat to false. After that, we have auto start, which I want to set to true. Finally, we have a function which by default gets none, so I want to ignore it. With that, we have a timer that runs for 1 second, and we can check if this timer is active or not. This we're doing inside of the while loop. All we want to do is print timer.active. Timer.active, which gives us this attribute. This is not going to work yet, because for the timer to work, we have to call the update method. This method here is super important. And for that, all you have to do is timer.update. And that is pretty much it. If I now run the thing, we're getting true, and after 1 second, false. Or in other words, the timer was active for 1 second, and then it deactivated itself. If you want to be a bit fancier, what you could also do is add a function, which is going to be the last argument. Let's call this one trigger timer. And make sure not to call this function. This happens inside of the timer itself. I only want to create a trigger timer function without any arguments, and if that is run, we are printing timer is triggered. This is now going to be executed after 1 second, or whatever value you set as the duration. So if I run this without the print statement, we should be getting, after 1 second, timer is triggered. And that is working pretty well. So with that, we have a timer. I think it's fairly straightforward in terms of usability. But let's do an exercise. I want you to create an instance of the sprite. And for the sprite, make the color change every 1.5 seconds. On top of that, change the position of the sprite rectangle every 4 seconds, meaning you are going to need 2 timers. Pause the video now and see how far you get. First of all, we have to create one instance of the sprite class, for which I want to create a sprite variable and then sprite with some random values. For the position, I want to have a list with x and y. Let's go with 0 and 0. For the size, I want to have another list with, let's say, 100 and 200. After we have that, I want sprite.draw. With that, we should be getting a rectangle in the top left. And we do. This by default is going to get a white color because that's the default value for the color attribute. But once we call randomize color, we're going to get something else. For example, if I call sprite.randomize color, we are getting a green color or anything other than white. This randomized color we want to call via the timer, which we can do quite easily. All we have to do inside of the timer class, and this we have to do after we created the sprite, is sprite.randomizeColor. For the duration, I have set this one to 1.5. If I run this again now, we are getting a new color every 1.5 seconds. Or actually, we don't, because the timer is not repeating. For that, the second argument needs to be true. Let's try this again now, and we're getting another color, and this happens multiple times. Besides that, I want to have another timer for the position, which should trigger every 4 seconds. This should be repeated, so true. It should auto start, also true. And the function I want to call is sprite dot, let's call it randomize position. This method doesn't exist yet, so I want to create define randomize position. No need for custom parameters, we only need self. And I guess this one should be right below randomize color, although the actual position of the method doesn't matter. To get random values, I need from random import randint. I want to update self.rectangle.x and give it a random integer. Let's say between 0 and 1800. That way, we are not going too far to the right. The same thing I want to do for self.rec.y with 0 and let's say 900. That way, we should be getting a new position every 4 seconds. Nearly done. The last thing that you shouldn't forget is that we have to call the update method on the timer pos as well. It means timer pos.update. And now this should be working. After 4 seconds, the position should change. And there we go. This looks pretty good. Let's wait for one more time and perfect. So with that, we have timers that can do any kind of logic, really whatever you need. Now, just to organize things a bit better, having these 2 timers outside of the class isn't ideal. What I prefer to do is inside of the class where you want to use them, you are adding self.timers. This is going to be a dictionary where we are going to need names for the timers. Let's call the first one color, and I just want to copy the timer itself, this one here. Besides that, I want to have one for the position, which is the other timer we have created. Now to work with these timers, I want to create another method, define, let's call it update with self and nothing else. And then for timer in self.timers.values. Don't forget to call this one. And then timer.update. That way we are updating all of the timers at once, which is a bit more elegant. After that, all we have to do is call this update method instead of these two. In fact, I want to comment out these two timers and these two timers. Instead, all I want to do is sprite.update, and that way we should be getting the same result. Although I think I realized this should be self.randomize color and randomize position instead of sprite, because now we are working from inside of the class. Once we have that, all of this should still work just fine, and that looks good. Perfect. It keeps on working. Great. So with that, you can add timers to any sprite class, or well, any class in general, and execute some logic, which is quite powerful. For the last part of the basics of Raylib, I want to work on animations, which are super important for any good-looking video game. For animations, the basic logic is quite simple, but the implementation can be a bit tricky. So let's talk about it. In the most basic sense, when we are working with animations, all that we are doing is play images in a sequence. Or in other words, if these are the frames of our animation, if you play them fast enough in sequence, we are getting movement. The basic logic is super simple. The difficulty is how to manage that many frames. Let's do this in VS Code right away. Here we are back in the code editor, and I am in 10animations.py, which at the moment doesn't do very much. We are simply getting a black window. We are doing the imports, we are initializing a window, then we are doing the while loop, and we're closing the window. The most basic setup that you can have. And for the animations, the first thing that you have to do is imports. In our case, we have an animation folder, which contains the animation frames. Those we have to import. We have to go from 0 to 7. Or in other words, inside of the code, we want to have the animation frames, which we can get via a list comprehension, where we want to load a texture with a path that comes in a second for I in range 8, which means we are going up to 8, but not included. As a consequence, for this range, our numbers will go from 0 to 7. This we can use to create a path using the join method. I first of all want to go to assets, then I want to go to animation, and finally, I want to create an f string using the I for the name of the file, and don't forget, we need .png. And then I forgot the I. This should now work. On the next line, I want to print the result, so animation frames. Let's run all of this, and we are getting a list with all of the textures. That works pretty well. This we could already use. For example, inside of the while loop, I want to draw a texture for which we first of all need a texture, which we can get from our animation frames, and then we have to pick one. Let's go with 0. After that, we need a position. Let's go with 0 and 0. And finally, a tint color, white. If we're doing that, we're getting a cowboy. And now, for the animation, we simply have to increase this value. If it's a 1, we're getting the next frame. If it's a 2, we're getting the frame after that, and so on. Once this value is dynamic, we are getting an animation. For that, the way I usually approach it is, first of all, I'm getting an animation index, which by default is going to be 0. And this value we are using to pick one frame. At the moment, this doesn't do anything because animation index isn't being updated. But that we can do before we are drawing stuff. All we need here is the animation index and then increase it by a certain amount, for which we could set an animation underscore speed. which I want to set to 5. After that, we need 5, and don't forget, this we have to multiply with delta time, so we are getting frame rate independence. To make that work, for delta time, I want get frame time, and then we're getting an animation index. This, however, is not going to work yet, because if we're doing this operation, we are getting a float, which cannot be used for indexing. To fix that, when we are getting the index, we want to convert this animation index to an integer. And with that, we should already get something. If I run the code now, we are getting an animation, but at some point it crashes. And I think you can see the reason why. This number keeps on growing forever, but animation frames has a finite number of entries. As a consequence, at some point, this integer becomes too large for the list, and the entire thing crashes. The way to fix that is when you're running this line, you want to add modulus length of the animation frames. And this should be properly called like so. If you're doing that, you are playing the animation forever. And that is working pretty well. Cool. With that, we have the most basic animation. That is basically all you need to get started with animations. Although for proper video games, you are going to end up with a lot of animation frames, so you really want to organize all of this well. Otherwise, things get very messy very fast. To practice that, let's do an exercise. I want you to create a sprite class with the animation, so everything is inside of one object. Pause the video now and see how far you get. I want to create a class animated sprite. As always, we will need a dunder init method without any arguments for this one. Most importantly in there, we will need these 3 things. I guess we can copy the animation frames, paste it in there, and then self.animationFrames. Besides that, I want to have self.animation index and self.animation speed, which are going to be 0 and 5. After that, I want to have an update method with self and delta time. For now, this one is not going to do anything. And then I want to have define draw, like we have seen before. I guess this is where we can start, because in there, I simply want to draw the texture. I can copy this line, paste it in there, and then we just have to add a few more minor things. This should be self.animationFrames, this should be self.animationIndex, and length of self.animationFrames. For the update method, I want to do these 2 lines. And well, delta time, we're getting from outside of the class, so I simply want to get this line. Although this should be self.animationIndex, and I just realized this shouldn't be a 5, this should be self.animationSpeed, and down there, this should also be animation speed. And with that, we have a very basic class that can be animated. All we need now is to comment out the stuff we have done earlier, this line, and this line. Instead, I want to create an animated sprite via the class. After that, inside of the game loop, I want to get the animated sprite and update it with delta time. And finally, animated sprite.draw. The end result should be the same. And it is. That's looking pretty good. Cool. And with that, we have covered the basics of animations. Alright, at this point, we have covered all of the basics of Raylib, which means we can create this spaceship game in 2D. That's going to be a really good way to combine all of the fundamental elements. For all of that, by the way, we have a project folder, which means inside of VS Code, you want to open Game2D, select this folder, and then you can see a couple of start files. We have audio, code, font, and images. This is going to be all we need for the game. There isn't very much code. We have inside of main.py, really just 2 import lines. Then we have settings, which does all of the imports and sets up a few basic constants for the game. Finally, we have the custom timer. This we have already seen. This is the project I'm going to work in just a second. First of all though, for this project, we are not going to learn anything new. You should be able to do most of this stuff on your own, which means there's only going to be one exercise for the entire project. And that exercise is to, well, create the entire project. I want you to create as much of the game as you can. Just try to get started and see how far you get. If you only get halfway, that is still totally fine. Just try to get started and see how far you get. If you want to make all of this a bit easier, you can download the finished project and take some ideas from that. Just make sure you don't copy-paste everything. That would be kind of cheating. So, pause the video now and try to see how far you get. Righty, let's do it together now. So, we have main.py, settings.py, and the custom timer. The custom timer we don't need for now. I only care about settings and main.py. For now, inside of settings, I only really care about window width and window height. This I want to use inside of main.py to create the basic window. Although the basic logic of the game, I want to have inside of a class called game. In there, I want to have a dunder init method with self and no other parameter. And in there, we can init the window, for which we need the window width and the window height. Along with a title, this could just be space shooter. Doesn't really matter that much. Besides that, I want to create another method called run. Once again, no need for custom parameters. All we want to do in here is while not window should close. Don't forget to call this one. And then begin drawing and end drawing. That way we can draw things on the screen. After the while loop is done, I want to close the window. That should be pretty much the most simple setup that we can go with. I want to create one instance of it. Game is going to be game and then game.run. Let's try this and we're getting a window. That looks pretty good. Although since we are going to work with multiple files, I want to do one more thing. If dunder name is equal to dunder main, only then do we want to do both of these things. That way we make sure that we only ever run this file and don't accidentally run something else. With that, we have the basic setup. So next up, we can work on the ship. For that, I want to create a new Python file called sprites.py. In there, we are going to have all of the objects inside of the game. First of all, in there, I want from settings and import everything. That way, we get access to all of these things, most importantly, PyRay. After that, I want to create a class called Sprite, which is going to be the parent class for basically everything in the game. I want to init it and then have the parameters self, texture, position, speed, and direction. All of these are going to be parameters, meaning self.texture is going to be texture, self.pos is going to be position, self.speed will be speed, and finally self.direction is going to be the direction. Besides that, for the parent class, I want to have an update method that has a custom parameter for delta time, although at the moment it doesn't do anything. And then I want to have a draw method that doesn't need any custom parameters. At the moment, it's not going to do anything either. This would be the parent class. From that, I want to create the player, which means it needs to inherit from Sprite. We will need dunder init, as always, with self, texture, position, and that's all we need for now. To initialize the parent class, I want to call super dunder init, and then we need arguments for these parameters. Let me copy paste them actually. Texture and position are super easy. Those we have by default. Speed, we are getting from settings because in there we have the player speed. Simply copy this one in there and then you're good to go. The direction for the player doesn't really matter. This one is set by user input, meaning this could for now be simply a vector2 without any values. That way, we have one class that can actually be displayed. And to display it, we want to look at the parent class and inside of draw texture v, where we are getting self.texture, self.position, and the tint color will be white. So with that, we should be able to display the player. We just have to get some kind of texture. Now you could import the texture right when you are creating the player. That would be possible, but not something I want to do. Ideally for a game, you want to have one dedicated place that imports everything, and that you are then working with inside of the game. Which means, inside of the game class, I want to create an import assets method. No need for custom parameters. All we want to do in here is create a dictionary called assets, where we, for example, have the layer texture, which we are getting via load underscore texture, for which we need join, and then go to images and spaceship.png, hence images and spaceship.png. That way, we have the texture for the spaceship, and that we can use to create the player. For that, first of all, we have to import the class, which means from sprites, import, I think I called this player. We are importing this class. After that, inside of the init, we have to call import assets. That way, we're getting this dictionary, and that means we can create self.player, which is going to be the player class, for which we are going to need one texture, self.assets and player. Besides that, we need a position, which has to be a vector 2, and I want this to be in the window width divided by 2 and window height divided by 2. That way the player should be right in the center of the window. Just to make sure that this is working, inside of the run method after begin drawing, I want self.player.draw. Let's try this now, and we can see the player roughly in the middle of the window. We are not precisely in the middle, because remember, we are placing the top left of the texture, which is a bit annoying, but I don't think it's a major issue. I'm not going to worry about it too much. Instead, I want to move the spaceship around, for which, first of all, inside of the player class, we will need an input method, which is something we have seen plenty of times by now. I want to get self.direction. This we're getting from the parent class. And for that, we want to get int is key down with key underscore right. And from that, we want to subtract the left key, which is the same line, except now it's going to be left. Oh, and also this should be self.direction.x. Because next up, I want to duplicate all of this and then cover the vertical axes, for which we want to get key down and subtract key up. Also, don't forget, you want to normalize the vector, which means self.direction is going to be vector to normalize self.direction. That way we always have the same speed. And I guess while we're here as well, I want to check if is key underscore rest with key underscore space. If that is the case, at least for now, I simply want to print laser. The functionality for that is going to come later. That would be all we need for input. To actually call this method, we have to override the update method of the parent class. There, we want to have self and delta time. That way, we are overwriting all of this and keep the same functionality, which at the moment is quite easy because update doesn't do anything. But in there, we want to get self.input and then call self.move with delta time. This move doesn't exist yet, and since we want to reuse it later on, it should exist inside of the parent class. That means I want to create define move with self and delta time. This logic we have seen as well a couple of times by now. We want to get self.pos.x plus equals self.direction.x multiplied with self.speed and multiplied with delta time. That would be the horizontal movement. For the vertical one, self.pos.y multiplied with self.direction.y and then speed and delta time. That way, we have the move method. which should be enough to move the player around. All we have to do before we are drawing anything is call self.player.move with delta time, which we don't have at the moment, but we can get it very easily. Delta time is going to be get frame time. And oh, that was a silly mistake. This shouldn't be move, this should be update, because we want to call both input and move. And this is working, although I think I forgot something. Before we are doing any kind of drawing, I want to clear the background, for which we have a color inside of our settings, BG color. This I want to use in there. That way we have a slight purplishy color, and now we can move around, and this works just fine. Perfect. That would finish the player, although there's one more thing that I do want to do. If we move too far to the right, we can leave the screen, which doesn't feel like a good experience. That we can fix very easily. Inside of the player, I want to add one more method, define constraint. No need for custom parameters. All we want to do in here is self.pos.x is going to be max with 0, and then minimum self.pos.x and window width. That way we can never go below 0 or beyond the window width. Although this doesn't work yet, if I call self.constraint and run main.py again, the left side should work just fine. And it does. That looks good. However, on the right side, this doesn't work yet. Because remember, we are placing the top left point. And for that point, we are checking if we are on the right side of the window, which means the entire rest of the ship can be to the right of that. Not ideal, but we can fix that. And for that, I want to work inside of the parent class. In there, we can get self.size, which is going to be a vector2 in which I want to get the texture.width along with the texture.height. And that way we know how large the texture is going to be. If I print the result, self.size.x and self.size.y, you can see the result. If I run main.py, we get the width and the height of the ship. That we can use inside of constraint. The maximum value should be window width minus self.size.x. Let's try this one again, and now the ship is going to stack to the right side of the window. That looks good. The same thing I want to do for the vertical axis, which means self.pos.y is going to be max 0, self.pos.y, and then window height minus self.size.y. Next attempt, and now we have a top constraint and a bottom constraint. That means next up, we can make the entire thing look a bit better by adding stars to the background. For that, first of all, I want to import star.png, a super simple file. This happens inside of the import method. I want to duplicate the line and get this star, which is going to be images and star.png. For all of these stars, I want to have a random position and a random size. This we have to do somewhere before we are actually running the game. I guess we can do it below self.assets, although it's not the perfect place, but good enough for our purposes. I want to have self.star_data, which is going to be a list comprehension. I want to create a tuple with two parts. The first one is a vector2 with x and y. Both of those are going to be random positions, which means I want to have randint, something we are importing inside of settings here. The values are going to go from 0 to the window width. That's going to be x, and for y, I want to have randint from 0 to window height. That covers the position. Next up, I want to have the size, and this we are getting via uniform, where I want to have values between 0.5 and 1.2. In other words, we get half the size or a 20% increase. All of this we want to do for I in range, let's say 30. Just to make sure this is working, let's print self.star_data. If I run this again, we are getting a list where we have a vector and then a floating point for the size. That means now we just have to draw everything. For that, I want to have a dedicated method, draw stars. No need for custom parameters. I simply want to get for star in self.starData, in which I want to use draw texture x, because in there we can set a rotation and a scale, both of which have to be floating point values. First of all, for the texture, I will need self.assets and star. After that, we have the position. This is going to be star 0, the first item in the tuple we have just created. Afterwards, we have the rotation. This can stick at 0. And finally, we need a scale, which is going to be star 1. This value here, which I should add a comment to size. Finally, we will need the tint color, which is going to be white. That way we are getting the stars, which we want to draw before we are drawing the player. Self.draw stars. And now we are getting loads of stars. I guess we could change the scaling just a bit. Let's do maybe something like 1.6. Looks a bit better. Just play around and see what you like. In my case, I am happy with that, so we can continue. Which in my case for now is going to be cleaning up this code just a bit. I want to separate the run part into 2 extra methods. I want to have an update method without any custom parameters. And there I am doing these 2 bits for now, where we are getting delta time and update the player. This we can call in here self.update. And besides that, I want to have a dedicated draw method in which we are going to do all of this. Make sure you have the right indentation. That way you can simply call self.draw and you should be getting the same result, except now we have everything just a bit cleaner. Next up, I want to work on the lasers, which we are creating whenever the player presses space, which I haven't tested yet, but inside of the game, if I press space, we're getting laser. That looks good. Also, I don't want to print the size of the sprite that we are creating. Righty. First of all, whenever the player is pressing space, we want to create a laser. But for that, we have kind of an issue at the moment. And that is inside of main.py. We want to have all of the lasers, but we get the input inside of the player, which isn't really a good place to store these lasers. Which means effectively, inside of main.py, I want to create a method that creates the lasers, and this method will be called inside of the player. In practice, this means, let me create another method. I guess we can call it shoot laser, for which we will need self and a position parameter. For now, I simply want to print create laser in here. This shoot laser, we have to pass into the player class, this one up here, as another argument, self.shootLaser. For that to work though, inside of the player, we need another parameter for the dunder_init class, shoot laser. This I also want to store as an attribute, self.shootLaser is going to be shoot laser. Make sure to never call the method at this point. This we want to do down here when the player presses space. I want to call self.shootLaser with a position, which is going to be a vector 2. For now, let's say 1 and 2, so we know what we are getting, which we can test right away. Besides create laser, I want to print the position. If I now run the game and I press space, we get create laser along with a vector 2 for the position. That looks good. That means next up, we can create a laser sprite, which we do below the player, class laser. Once again, the parent will be the sprite class, and we will need a dunder_init method where we have self, a texture, and a position. This we are going to use with super dunder_init, for which we have to reuse the texture and the position. So once again, we want to get these 4 parameters. The speed for the laser is going to be the laser speed. This we have set inside of settings. This one here. For the direction, this part is quite easy. The laser is always only going to go in one direction. 0 and -1. That way, we are only going up. So, next up. Whenever the player calls this method, we want to create one instance of a laser. For that, at the top, we have to import the laser class. And then, instead of printing things, I want to create one instance of it. For which, first of all, we will need a texture, which we get from the assets dictionary. In there, I want to create a laser, which I believe we are getting from images and laser.png. This file here. That's the first part. I want to get self.assets and laser. Next up, we need a position that we're getting from the parameter. Although at the moment, this is very hard to see, since the position we're getting from the player is 1 and 2. That's going to be right in the top of the window. To make this a bit more visible, let's go with 1600, roughly in the middle of the window. That should already work, but we are not going to see anything. If I try and press space, at the very least, we are not getting an error, but we cannot see the lasers. And that is because for the laser, we are never calling any kind of draw or update method. Hence, they're not going to be drawn. For that, we need some kind of way to access this sprite. Since we are going to have many of them, this should be some kind of list. In my case, inside of the init method of the game class, I want to create self.lasers, which is going to be an empty list. And then, when we're creating one laser, I want to get self.lasers and append the laser that we have created. After that, we can work inside of the update and the draw method of the game class. For update, I simply want to, for laser in self.lasers, and then laser.update, and don't forget delta time. For the draw methods, I want to get for laser in self.lasers, and then laser.draw. That way, I can run the game and press space, and we're getting one laser. If I press it multiple times, we are going to get multiple, but you cannot see that, because they're all in the same position, which we should fix right away. Whenever the player is creating a laser, this position should be flexible. It should always be in the middle and in front of the player, which means for x, I want to get self.pos.x plus self.size.x divided by 2. For y, I want to have self.pos.y and then subtract, let's say, 20 pixels. Remember, self.pos.y is already at the top of the player. I am simply subtracting 20 pixels to have a bit more of a distance between the player and the laser. This number might have to become a bit larger, but let's play around with it. If I now run main.py, we're getting a laser that is in front of the ship, although a bit too close to the player. This we can fix by changing this 20 to a 50. Next attempt, and this looks a bit better. And if you look very closely, you can see that the laser is not exactly in the middle of the player. That happens because we are placing the top left of the laser, which for a real game would be a bit annoying, but once the lasers are moving, this is not going to be noticeable. In fact, let's work on that, although first of all, I want to increase the distance even more to, let's say, 60. Next up, we want to move the laser. That will happen via the update method. In there, I want to call self.move with delta time. Since the laser has a direction and a speed, this should work already. If I now run all of this again, we are getting a moving laser. So that is working pretty well. Now this works, but there's a major flaw. We keep on creating lasers, but we never get rid of them. As a consequence, if I print length of self.lasers and I run the game, I can press space as often as I want. We keep on adding lasers. Theoretically, we could create infinite ones, and this would be a major drag on performance, which obviously isn't good. you never want to have a system that creates infinite anythings. In our case, we want to get rid of a laser if it leaves the screen, which I'm going to create via a check_discard method. No need for custom parameters. All we want to do, we want to update some kind of discard attribute, which is either going to be true or false. In my case, I want to check if the ship is outside of the values -300 and +300. Or in other words, if this is the window, I want to check this border here, which would be -300, and the border down here, which is +300. Anything that goes outside of these two borders should be discarded. In other words, I want to check not -300 is smaller than self.pos.y is smaller than window height plus 300. Also, self.discard should exist whenever we create one instance of the class, which means self.discard by default is going to be false. That way, we can check if a sprite should be discarded or not. This is going to work for the lasers and for the meteors. Although for that system to work, inside of main.py, we have to add one more check, for which I want to create another method, define discard sprites. For example, for the lasers, I want to get self.lasers and then create a list comprehension. I want to get laser for laser in self.lasers. That way, we would simply copy the list. To then get rid of the lasers that we don't want to keep, I want to add if not laser.discard. That way, we are getting rid of all of the lasers that have discard set to true. This we now have to call before we are updating all of the lasers. I want to call self.discard sprites. To make sure this is working, let's print the length of self.lasers. And then we can test this. Although I realized inside of sprites, we also have to make sure that inside of update, we are calling self.checkDiscard. Let's try this now, and I can shoot as fast as I can, but we never get beyond 7 lasers. I guess if I press really fast, we might get to 8, but you get the idea. This system works, which helps a lot to maintain performance. And that covers the basics of lasers. Later on, we have to revisit them for collisions, but that's not an issue for now. Instead, I want to work on the meteors, for which, first of all, inside of import assets, I want to import the texture, which means in our entry, meteor, we want to go to images and meteor PNG, which will give us this PNG file. Besides that, I want to create a meteor via a timer, which I want to create inside of the dunder init method. All we have to do in here, let's do it below the lasers, self.meteor_timer. For that, we're going to use the custom timer class, the one I have talked about earlier, and then set a couple of values. First of all, the duration. This we are getting from settings, meteor timer duration. This should be repeated, it should auto start, and once it is done, we want to call self.createMeteor. Make sure not to call it. This is going to happen inside of the timer. So next up, we have to create the method createMeteor. No need for custom parameters. For now, all we want to do in here is print createMeteor. To make all of this work, we have to make sure that we are updating this meteor timer, which happens inside of the update method. Let's do it before we update anything else. Self.meteortimer.update. And now we get create meteor every, I think it's 0.4 seconds, or whatever you set in here. Next up then, inside of sprites, we have to create another class for the meteor, which once again has the sprite as the parent. Just as before, we will need a dunder init method with self, and the only thing we need in here is a texture. You'll see in a second why. But first of all, we want to call super dunder init where we are getting all of the parent parameters, these four, and I want to paste them in there. The only one that we are getting already is the texture. Besides that, we need position, speed, and direction. Let's go through them one by one. First of all, I want to have a position, which is going to be a vector 2 with x and y. For both of those, I want to have a random integer. For x, it's going to be 0 and the window width. For y, it's also going to be a random integer, although for this one, I want to go from -150 to -50. That way, we're getting a random value above the window. Besides that, I want to have the speed, which is also going to be a random integer that is going to go between these two values, meaning the meteor speed at the slowest is 300, at the fastest it's 400. To get both of these values, I simply want to unpack meteor speed range. Finally, we need a direction, which once again is going to be a vector 2 with x and y. For y, we always want to have 1. For x, I want to create a random floating point value via uniform with a value that can go between -0.5 and 0.5. With that, we have all we need for the parent class. So next up, inside of main.py, I want to import the meteor class. And then whenever we are creating a meteor, I want to create them like we have done for the lasers. Which means whenever I am creating a meteor, I want to add it to a list and then update and draw every element inside of that list. In practice, that means besides self.lasers, I want to have self.meteors, which is going to be another list. To that list, self.meteors, I want to append the meteor that we are creating, for which we only need a single argument, which I can copy to save me some typing, self.assets meteor. That should be a good start, and like for the lasers, inside of the update and draw method, we have to update and draw all of them, which you could, for example, do with for meteor in self.meteors and then meteor.update with delta time. The same we want to do inside of the drawing part for meteor and self.meteors, meteor.draw without any arguments. And now we should be getting meteors, and that looks about alright. We are going to refine this just a bit by adding rotations, but for now, it's not too bad. First of all though, these for loops don't feel elegant. A better system I feel would be for sprite in self.lasers plus self.meteors and then sprite.update with delta time. That way we can get rid of these two for loops and we should get the same result. Let's try, and I can still shoot lasers. We're getting moving meteors. That looks good. That means the update method is still being called on everything. The same thing we can do inside of the draw method for sprite in self.lasers plus self.meteors. Sprite.draw afterwards, then we can get rid of these lines, and we have made the code just a bit more elegant. To make the meteors a bit more interesting, I want to add rotations. For which, first of all, we will need self.rotation, which by default is going to be 0. This value should be updated, for which we want to call the update method with self and delta time. First of all, in there, I want to call super and then update with delta time, so we keep on getting this functionality, which we don't want to change. But on top of that, I want to get self.rotation plus equal, let's say 50 times delta time. The rotation speed you could customize, but in my case, I'm not too concerned. This at the moment doesn't do anything though, since we are simply updating some kind of value, but we are not using it. To actually use it, we also have to override the draw method. To draw something with a rotation, you need draw texture row, which wants to have quite a few different arguments. We want to have a texture, a source, a destination, an origin, a rotation, and a tint. The texture is quite easy. We simply want to keep self.texture. Then we need two rectangles, a source and a target one. For the source, we want to have one rectangle that cuts out a part of the texture. Since we want to get all of the meteor texture, this source rectangle should be the size of the texture itself, which we can get quite easily. Let's call it self.rect, and this is going to be a rectangle with 0 and 0, and then self.size.x and self.size.y. This we can now use with self.rect down here. Next up, we need a destination rectangle. This is where we are going to draw the actual texture. For that, we will need a target rectangle, which once again is going to be another rectangle, which has to be the actual target position, which means I want to have self.pos.x, self.pos.y, self.size.x, and self.size.y. This we now want to use for the next argument. That way we have both of the rectangles. Then we want to have an origin point. This is basically the point we are going to rotate around, which in my case is going to be a vector 2 with self.size.x divided by 2 and self.size.y divided by 2. After that, we can finally use the rotation, which is going to be self.rotation. Finally, we need tint, which will always be white. That is all we need down here, and VS Code is complaining about this line because I forgot a comma. Now this should be working. Let's try, and we are getting rotating meteors. Perfect. Now I guess Draw Texture Pro is a bit more advanced. You basically want to have a texture, and then a rectangle which cuts out a texture. And this cutout texture you are going to draw inside of a new rectangle. That's going to be the target rectangle. You're going to draw it around the point, and this you can rotate. I think if you play around with it for a bit, it becomes fairly accessible. So I hope this part wasn't too confusing. Now we have lasers and meteors, and that is a pretty good start for a basic game. Although next up, we need actual collisions, which we don't have yet at all. I guess to get started on that one, I want to create another method with check_collisions. For now, I don't want to do anything, but more generally, I want to create a collision between lasers and meteors, and between the player and the meteors. Those are going to be two separate systems. For these collisions to work though, we need a couple of shapes. For the meteor and the player, that's going to be a circle, and for the laser, that's going to be a rectangle. Remember, when we are working with collisions, we are checking the collision between simple shapes. That is much better for performance and much easier to implement. To get started, I want to work in the parent sprite class and add another attribute, self.collision_radius. For that, I simply want to get self.size.y divided by 2. This could, for example, be a meteor, and for this meteor, we have a width and a height. For the collision radius, the thing we have just created, I simply want to go from the center and then half the width. That way, we are getting a radius around it that we can use for the collisions. Same for the player, which is going to look something like this. We effectively are going to create a radius around the center of this player, which I think is the best shape. If we had a rectangle, something like this, we could work with that, but then we have these giant areas that are very easy to hit, which probably wouldn't feel good. Hence, I'm going to work with a circle. For that, inside of main.py, I want to start with the player and meteor collision, for which, first of all, I want to check all of the meteor. For meteor in self.meteors. To check this collision, all we need is check collision circles, where we want to get self.player and via a method get center. This we're going to create in a second, and then self.player.collision radius. Remember, for check collision circles, we need 4 arguments. The center and radius of the first circle, and then the center and radius of the second circle. We at the moment have only the player. Next up, I want to have meteor.getCenter And I want to have meteor.collision radius. If that is the case, for now, I simply want to print collision. For that to work though, we have to create a getCenter method, which is going to happen inside of the sprite class. I want to define getCenter. All we need in here is to return a vector2, where x is going to be self.post.x plus self.size.x divided by 2. We get the top left and then add half of the width. The same thing we want to do for y, self.post.y plus self.size.y divided by 2. That way, we get a center for both the player and the meteor. This method we now have to call. After we are doing the updates, I want to self.check collisions. If I now run all of this, we are getting collisions, and that looks pretty good. Cool. To keep the game simple, once we have a collision between a meteor and the player, I simply want to end the game, which means close_window. Next attempt, and now as soon as the player collides with a meteor, the game is over. Next up, to get the collision between the lasers and the meteors, we first of all need a shape for the laser. I want to create a method get_rectangle, which is going to return a rectangle with the position and the size of the laser, which means self.post.x, self.post.y, self.size.x, and self.size.y. Effectively, we are drawing a rectangle around the current position of the laser. That we can then use inside of check collision, and let's remove the pass in here. I first of all want to go through all of the lasers, which means for laser in self.lasers. After that, to get all of the meteors, for meteor in self.meteors. Now we have all of the lasers and all of the meteors. That means we can check a collision between a circle and a rectangle. First of all, we need the center and the radius of the circle, which means we want to have meteor.get_center, and we want to have meteor.collision_radius. Finally, we need the rectangle, which is going to be laser.get_rect. Make sure to call this one. That is going to return a Boolean value, and if that is the case, I want to discard both the laser and the meteor, which means laser.discard and meteor.discard are both going to be true. Oh, and something we haven't done yet, inside of discard sprites, we are never discarding meteors, which we can do quite easily. Self.meteors is going to be a list comprehension with meteor for meteor in self.meteors, but only if not meteor.discard. Let's try this now. I can shoot at meteors, and this kind of works, although it looks a bit weird. And if I hit a meteor on the left side, if I get one roughly here, this doesn't seem to work perfectly. This is because of this draw texture method, which draws the texture with the position being right in the middle. As a consequence, when we are calling getCenter, so define get_center, I want to override this method. Instead of adding half of the value, I simply want to return self.position. That way, all of this should work just fine. If I now shoot at a meteor, we are getting a much better behavior. Also, now the player gets a real collision. Once again, this method gets a bit more advanced. But basically now, since we are drawing custom rectangles, we have the position right inside of the center of the meteor. But anyway, with that, we have the basic collision logic. To make all of this a bit more visually interesting, I want to add another class. Effectively, after a laser hits a meteor, I want to play a short explosion animation, which is going to be another class, explosion animation. This one is not going to inherit from the sprite. That is because for all of the sprites, we only want to have a single texture. But for the explosion animation, we want to play an animation. So we want to work with multiple textures. As a consequence, for dunder init, I want to get self, I want to get a position, and then I want to get textures, multiple, which I want to store inside of an attribute right away. Self.textures is going to be textures. Besides that, I will need self.size, which is going to be a vector2, where we are getting the first texture, so texture 0, and then the width. The same thing I want to do for the height. Let me copy this and replace width with height. Once we have that, I can get self.position, which will be a vector2. But really important now, I want to place the center of this explosion animation, which makes the math a lot easier. For that, I want to get position.x. Remember, this is going to be the left side of the texture. From that, I want to subtract self.size.x divided by 2. For position.y, I want to do basically the same thing. Self.size.y divided by 2. And this I want to subtract from this value. That way, we should be placing the center of the texture. In fact, I want to define a draw method where we are drawing a texture v with self.textures, and we have to pick one, which I want to do via integer and then self.index. Self.index doesn't exist at the moment. This we can change quite easily. Self.index will be 0. For the position, I want to have self.pos. For tint, we are going to use white. That should do something, but inside of main.py, we first have to do all of the imports, which happens inside of import assets. In there, I want to add another entry called explosion. This is going to be a list comprehension in which we want to load a texture via a path that I'm going to create in just a second. First of all, though, we want to do for I in range, and then we need a number. If you look at images, explosion, you can see we have 28 images in there, starting from 1 and going to 28, which means we want to go to 1 and up to, but not including 29. That way, we're getting all of these numbers. From that information, we can create the path using the join method. I want to go to images. Then I want to go to explosion. I believe I called this one. Yep, explosion. And then in there, I want to create an f string where we have i.png. I being a value between 1 and 28. That is going to give us the texture. Next up, to actually use it. First of all, we have to import the explosion animation. After that, like we have done for the laser and the meteors, I want to add self.explosions. Once again, this is going to be an empty list. Every value inside of this list we want to update and draw, which happens here and here. In practice, this means we want to simply add plus explosions to both of them. Like so and so. The last thing we now need is whenever we have a collision between a laser and a meteor, I want to create one instance of this explosion animation, which means self.explosions.append, and I want to append an explosion animation, for which I need a position and the textures. Position we're going to cover in just a second. First of all, though, textures is easy, self.assets and explosion. For the position, let's do this one actually in a separate variable, position vector2, so we have a bit more space. I need an x and a y position. Remember, those by default, if we simply got laser.pos.x, would be the left side of the laser. From that, I want to subtract laser.size.x. That way we should be going to the middle of the laser. For y, I want to keep 0. Let's try all of this, and if I hit a meteor, we're getting an error because explosion animation has no update method. That's totally fine. Inside of sprites, I want to define an update method with self and delta time, although for now it doesn't do anything. If I now run this again, I can shoot at the meteor, and we are getting pretty much nothing. That is because the first image of the meteors, 1, is very, very small. I guess if we play the entire animation, this should become more visible. For that, I want to first of all check if self.index is smaller than the length of self.textures minus 1, so we never exceed the length. If that is the case, self.index plus equal 20 multiplied with delta time. That way, we are simply increasing self.index that we are using to pick one of the textures. If, however, we are exceeding this value, meaning we are outside of the length of the textures, then I want to set self.discard to true. And at the moment, the explosion animation doesn't have self.discard, which means self.discard by default is going to be false. With that, back inside of main.py, under discard sprites, I want to do the same thing we have done already. Self.explosions is going to be explosion for explosion in self.explosion, but only if not explosion.discard. Righty, with that, let's try this again. And if I shoot a meteor, we still can't see anything. Or actually, if you look at the top of the window, you can see there we have the actual explosion. The issue we have at the moment is that when we set position 0, we are placing the explosion right at the top of the window, which obviously isn't correct. This should be laser.pos.y. Next attempt, and now if I hit a meteor, we are getting an actual explosion in the right position, almost. Although this isn't perfect yet, because I want to subtract laser size.x and divide it by 2. Let's try this again now, and that feels better. Once again, you can fine-tune all of this quite a bit, but for my purposes, I think this looks alright. Cool. With that, we have the explosions. That means we are nearly done. For the next part, I want to work on the score, so that we can see for how long we are surviving. For that, first of all, I want to load a font, which I guess we can put inside of assets. In there, I want to have the font. We're getting this via load underscore font, for which we need a file path. So I want to go to the font folder, and in there we have stormface.otf, which means I want to have font, and the next argument is going to be stormface.otf. To display that information, I want to create another method, define draw score. No need for custom parameters. All I really want to do in here is first of all get the score itself, which is going to be an integer of get underscore time, which will tell us how much time has passed since we started our game. After we have that, I want to draw text. Now we have to choose from one of the options. Draw text by itself is no good because we cannot use a custom font. Draw text X is going to be a bit better because in there we can set a custom font. Let's start with that one. For the font, I want to use self.assets and then get the font. For the text, I want to have the string of the score that we have just gotten. For draw text X, the second argument for the text itself always has to be a string. And at the moment, this value is an integer. This we have to convert. After that, we need to have a position, which for now, I want to be in, let's say, a vector2 position of 0 and 0. We'll update this in just a second. Then we need a font size, which I believe we have inside of settings. We have a font size. This I want to copy, 120. For spacing, I want to go with 0. And finally, we need a color, which I think I've simply set to white. This draw score we now have to call, which I want to do after we are drawing the stars, but before we are drawing anything else. That way, the meteors and the ship are on top of the score, which I think is a nice detail. Self.draw score. We have to call this, and now in the top left, we're getting the score. Now, there are two problems. Number one, we have to update the position. And number two, if I run this again, this font looks terrible. It looks like it was scaled up by a lot, which is true because, well, it has. When you are creating a font and the font size is getting too large, in our case, for example, this is 120, then Raylib is getting a bit weird. The way around that is when you are importing the font on this line, besides load font, you can also load font X, which lets you size a custom font size when you are importing the font. Then you need a few more arguments, which also get a bit weird, but we can work with it. First of all, we need a path. This one stays the same. Then you need a font size, which in our case is going to be the font size from the settings. So the one we have already seen. After that, we need code points and code point count. For those, you need ffi.null, which is part of Raylib and a way to say that we want to have a null value. A bit weird, but just go with it. For the code point count, we just want to have an integer, which can be 0. If I now run this again, our font is looking significantly better. And this is one of the few parts that I haven't explained before. Sorry about that. Anyway, with that, we have a much nicer looking font. We just have to center it now. For that, I want to get the text size first of all. And if you look at the documentation, you can find that we have measure text, but this one doesn't let us set a custom font size. So measure text X, and in there, we want to have the font, self.assets and font. Then we want to have the text string. This is going to be str score. Then we need a font size. This is going to be our font size. And finally, spacing is going to be 0. That way, if I am printing the result, text underscore size, we're getting a vector 2 with the width and the height of the text, which is perfect to center it inside of the window. Or in other words, for the position, instead of 0 and 0, I want to get window width divided by 2 and then subtract text size dot x divided by 2. For y, we can be a bit more relaxed and simply say this is going to be 100, so we have a bit of space to the top. Let's try this now, and the score is right in the middle of the window. I can also fly on top of it, and that looks pretty good. Cool. That is going to give us our score, which means we are nearly done. The last part that we have to work on is going to be the sound. For that, first of all, inside of the init method, after we're initializing the window, I also want to init an audio device. Besides that, to close the loop, after we have finished running the game, I also want to, before closing the window, close the audio device as well. And we can remove a bit of white space here. Not really necessary. That means we can now play some music. But for that, first of all, we have to import things. And that means inside of import assets, I want to create another dictionary. Let's call it audio. This is going to work just as before. I want to have a dictionary with key value pairs, where the key is the name of the file and the value is the actual audio file. I want to have laser, and this is going to be a sound file, which means load sound. The path we are getting from join, where we want to go to audio, and then to laser.wav. Just to double check, laser.wav. That looks good. I guess we can import all 3 of them at the same time. Besides laser, I want to have explosion, which is called explosion.wav. And finally, I want to have the music, which needs to be a sound file, which means I want to load a music stream. Using the same format for the path, join audio and music.wav. Make sure you're spelling this correctly, then it should be working. To get started, I want to play a laser sound whenever we are creating a laser, and the explosion sound whenever a laser collides with a meteor. That is going to happen, first of all, inside of shoot laser. Whenever we're doing that, I want to play the laser sound, meaning I want to play sound and self.audio laser. Let's try. That works. Cool. And next up, for the explosions, I want to check collisions. Then whenever a laser collides with a meteor, I want to play another sound from self.audio and explosion. That should be all we need. Let's try this again, and cool, that works. The final part now is that we have to play the background music. Inside of Thunder Init, I want to play a music stream. Self.audio and music is the file I want to play. Then inside of update, we have to update the music stream. Update music stream with the same file, self.audio and music. After that, for the final part, when the game is over, we want to get rid of this music stream, which means I want to unload a music stream with, once again, the same file. With that, we have the finished game. And this is going to be a slightly larger project, but I hope it wasn't too complicated. I think most of these parts are really simple. The one complication was the meteor, where we are using Draw Texture Pro, which does get a bit more advanced. Anyway, with that, we have covered the 2D part of this video, which means next up, we can work in 3D. So let's get started with 3D game development. To cover the basics, we are going to do 3 things. Number 1, we will create basic shapes. 3D shapes to be specific. We are going to give them random colors, and we are going to move them. Once we have all of that, we can work with imports and collisions, but that's going to come later. First of all though, we have to talk about 2D versus 3D. And most importantly in there, the majority of things stay the same. The basic game logic, where you have a game loop, you take input, and things like a camera stay pretty much exactly the same. Meaning what you have learned so far will still be very relevant. Besides that, you have lots of things that change slightly. For example, movement is now done via a vector 3 instead of a vector 2, because we have 3 dimensions. Things like collisions, because of a third dimension, become a bit more complex, but that's a fairly minor part. If you understand 2D collisions, 3D ones shouldn't be too hard. The only things that are going to be entirely new are 3D objects and shaders. Those I haven't covered yet at all. Shaders in particular are getting really advanced really fast. So those I am only going to cover on a very surface level. In case you don't know what those are, don't worry, I will explain. First things first though, let's start with basic objects. And for all of that, I have a new project file. Meaning you want to get Visual Studio Code and open a folder. The folder I'm going to work in is called Basics 3D. So select this folder, and then you are getting a couple of things. You get 4 Python files that I am going to go through step by step. Besides that, you have 2 folders, one with models and one with shaders. Sadly, you don't get a preview when you click on them, but you'll see later what they do. For now, don't worry too much about any of this. Instead, and I guess we can start right away, I want to work in one base Pi. In there, at the moment, we are not doing very much. Just as before, we have the basic imports, we are initializing a window, and then we have the game loop, in which we get delta time, we are drawing a white background, and then we begin and end drawing without doing anything. Pretty much the simplest project you can create. As a result, we're getting a white window. To draw anything in 3D, inside of the drawing bit, you have to enable the 3D mode. which you do with begin mode 3D, for which you will need a camera. That we're going to create in just a second. Besides that, after you finish drawing 3D stuff, you want to end mode 3D, which doesn't need any arguments. Between these two lines, we can display 3D objects. Although for that, first of all, we are going to need a camera, which we can create quite easily. We have seen this part before. I want to have a camera inside of a variable. Really important now, we want to create a camera 3D, not 2D. Which most importantly means when we set, for example, the camera position, we do not want to set a vector 2, we want to have a vector 3, where we have x, y, and z. I talk about these axes later on in a bit more detail, but basically x gets you left and right, z gets you forward and backwards, and y gets you up and down. So for example, in my case, for x, I want to have 0, for y, I want to have 5.0, and for z, I want to have 5.0 as well, meaning we are going up and off center by a certain amount. The same thing we have to do for camera target. This also needs to be a vector 3, which in my case should point at position 0, 0, and 0, which are the default values. So this can stay empty. This camera I now want to place inside of begin mode 3D. I want to have my camera in there, and if I run things now, we still can't see anything. That is because we're not drawing anything at the moment, which I think makes sense. Now, the simplest thing that you can draw inside of 3D is a basic grid for orientation. This you do with draw grid, and then you need slices and spacing. In my case, I want to go with 10 and 1. Although, if I run this now, we cannot see anything. That is because the camera is going to need just a few more things. First of all, for some reason, the camera needs to know where the up direction is, which we get with camera.up. In most cases, this is simply a vector 3 with 0, 1, and 0. Wherever you set the 1, this is going to be the up direction. Why that is necessary, I have no idea, but you do have to include it. Besides that, we want to have a camera.field of view for y. This tells you how wide the camera is going to be, which usually is 45.0. Once again, I'll play around with these numbers in just a second. Finally, we will need a camera.projection. This needs a constant, and that is camera underscore perspective. If I now run this again, we can see a grid, which is defined by these numbers. For example, if I change the 1 to a 0.5, then this thing becomes a lot smaller. Effectively, we are drawing a grid that is 10 by 10 fields, and each field gets a size. At the moment, that is 0.5, and we got 10 cells because of this 10. I think that part is fairly straightforward. And while we are here, we can also mess with this number in particular. If I set this, for example, to 20, then we are zooming in quite a bit. If I set it back to 45, you can see the difference. There we go. And if I set this to, for example, 90, then we are zooming out a lot. Although this isn't really a zoom, it's more of a change in the field of view. Once you have a bit more experience, you can play around with this one, but for now, I want to keep it at 45. Besides that, we have the camera position, which at the moment is 0 for x, 5 for y, and 5 for z. If I change y to, for example, 1, then we are much lower, and if I make it at 10, then we are much higher. I want to keep it at 5 though, and if I change the z parameter to a 1, then we are much closer to the center. I guess once we have actual objects, you can see this much better. Speaking of which, let's create some. I want to create a couple of basic models. The way that works in Raylib is, first of all, you have to create a mesh, which I want to store in a variable. And this you do via gen underscore mesh, and then the shape that you want to create. I guess a really easy one would be a cube. For that, we need a width, height, and length. To get started, let's go with 1, 1, and 1. This would give you a mesh, but that you cannot draw right away. Instead, you have to create a model, which you do with load model from mesh, for which we want to have one mesh, which we already have, the mesh we just created. This model you can actually display, which I want to do inside of the 3D mode, draw model with the model that we already have, and then we need a position, which needs to be a vector 3, which for now is going to be 0, 0, and 0. Besides that, we want to have a scale, which I want to leave at 1, and then a tint color. Let's go with red for now. Once you have all of that, you are getting a 3D object. Super important to understand right now is that when you are setting a position, you are always setting the center position of this object. Or in other words, you can already see that we have the same distance to the left and to the right. And if I now move a bit closer to the center on the z-axis, you can see this a bit better. We have an x-axis and we have a z-axis, with the center point being right in the middle. Once again, to understand all of this much better, you want to look at the documentation. If you scroll down quite a bit in there, at some point you find R models. This contains all of the 3D stuff. For example, you can draw some basic shapes. You can draw a model. This is what we have already done via draw model. And you can work with meshes down here and also import things. That we're going to cover in the next part. First of all, though, I want to do an exercise where you figure out one of these methods. I want you to draw a 3D line from position -4, 0, and -2 to position 5, 2, and 3. On top of that, the line should be black. Pause the video now and see how far you get. Back in the documentation, I simply want to draw a line 3D, for which we need a start position, an end position, and a color. And then we are good to go. Inside of the 3D bits, I want draw line 3D. For the start position, I want to have a vector 3 with -4, 0, and -2. The end position is another vector 3 with 5, 2, and 3. And finally, for the color, I want to have black. Let's try this now. And there we have a line going from one point to another. A bit hard to see because we are very close to the center on the z-axis. Let's change this back to 5 and they can see it a bit better. I guess if we go down on the y-axis to a 1, this should be more visible. And yeah, this looks about alright. Cool. So with that, we can draw a random object and we can create a model with a mesh. That means you already understand a couple of basic parts of the R model section. Although to really understand what's going on here, I want to talk a bit more about 3D objects. Now, when we had images for 2D games, those were really simple. We basically just arranged a whole bunch of pixels inside of a grid. That's all that PNG or JPEGs are. 3D objects get quite a bit more complex. Most importantly, their shape is defined by points, and those points are called vertices. These vertices can then be connected via edges, and to connected edges, you can assign a face. This face is what is actually visible to the player. And I'm fully aware this is going to sound super confusing, so let's do this a bit more practically. Here I am in Blender, which is a very popular 3D editor, and at the moment I have a cube open. By the way, Blender is entirely free, and it's really, really fun to work in it. If you're interested in 3D game development, you definitely want to check it out. Anyway, this cube is defined by a shape, and this shape we can visualize like this. The yellow dots are all of the vertices, these points here, and for a cube, we're going to need 8 of them. There's one in the back that you can't see at the moment, but it's definitely there. Some of these vertices are then connected to others. For example, this vertex is connected to this one here, this one is connected to this one, and so on. For some, we have a connection, for others, we don't. For example, between this vertex and this vertex, there's no edge, which is totally fine. Finally, Once you have enough edges, for example, for this side, we have one edge, we have another edge, then we have an edge here, and finally, we have one edge here. These four edges combined give you a face, and this face is what is actually visible to the player. We can also assign a color to it or a texture, then you could make it look even better. But that is fundamentally what we are doing in 3D game development. We are creating a shape via vertices, we are connecting some vertices via edges, and then to some edges we are adding a face. And this face is what's actually visible. And generally speaking, the more vertices you have, the better your game is going to look. Although, on top of that, the more vertices you have, the more difficult it is to run your game. So you do want to be careful, but for a basic game, this isn't really a concern. Let's say we want to create another shape. Specifically, I want to create a cylinder, for which, once again, I want to create a mesh, and this should be for a cylinder. This we create via gen mesh cylinder. For that, we need a radius and a height. Let's say for those, I want to have 1 and 2. I think those numbers are very simple. But then we have slices. For now, I want to set this number to 4. You'll see in a second what this one does. Once we have that, I want to create another model for the cylinder, which we once again do via load model from mesh with the mesh cylinder. This I now want to display. Instead of the model that we have used earlier, I want to display the model cylinder. If I run this now, we can't really see what's going on. For that, I want to move the camera up just a bit to 5 and 5. And there we have gotten, well, another cube. This isn't actually a cylinder. A cylinder is actually supposed to look round like this, and then you have the height that defines how long it is. Effectively, a cylinder is a tube, which we don't get, and that is because we are not defining enough points. Or in other words, to create this circle for the shape, we have to get loads of points to define this circle, which we are not doing at the moment. We are only giving Raylib 4 points to define a circle, which means it tries to do 1 point here, 1 point there, 1 point there, and 1 point down here. And those are getting connected. As a consequence, we are getting a cube. However, if I change this number to, let's say, a 50 and run this again, now we have a round object. But this we only get because we have many more points to work with. So be careful here, especially when you're creating round objects, you need a lot of points. But other than that, this is basically the way you would create a mesh and a model, which you can then display. Also, just as before, you always have variations on these functions. A really visible one for draw model would be draw model wires, which wants to have the same arguments, but if you run it, you are drawing the vertices and the edges, but not the faces, which for debugging purposes is super helpful. There you can see we have lots of stuff. If I change this for the mesh from 50 back to 4, then you can see really well what's going on. I guess for this one, we could go with 30. We don't really need that many points. Could even be 20. You get the idea. I think this is still good enough for a circle. Although in my case, I want to draw the thing with the faces, like so. Nearly done. The last thing that we have to do is to apply a texture. Because at the moment, this thing is pure red, which doesn't really look that good. But we can simply assign a texture to be drawn on top of all of the faces. For that though, we need some kind of texture, which we can generate right inside of Raylib. Although for that, first of all, we have to create an image, which we can do with gen, image, and then you get a whole bunch of options. You could create a basic color, although that's very boring. I want to create a linear gradient, which means we are transitioning from one color to another. Now for this though, first of all, we have to define the width and the height of the image that we want to create. And for that, we're working in 2D. This number doesn't really matter. Let's go with 20 and 20. Then we need a direction. This could simply be 1. And finally, we need a start and an end color. For the start color, I want to go with red. For the end color, I want to go with yellow. After we have that, we have to create a texture from the image, which we have already done, load texture from image with the image we have just created. After we have that, we can set a material texture, for which first of all, we need a material that we are getting from the model cylinder at the moment. In there, you can get the materials. A model can have multiple materials, but most of the time you only have one, and this you assign via indexing, so index 0. After that, we will need a map type, which in my case is going to be material, map, and then we want albedo. This defines the color of a texture, which is the one you basically always want to start with. But besides that, you could also set how metallic an object looks, you could set a height map or normal map or roughness map, and those determine how light reflects from the object. Although those are getting a bit more advanced, for the basics, you always want to go with albedo. Finally, we need a texture, and this is what we have just defined, this line here. With that, if I run this again, we can see a very slight difference. That is because when we are drawing the model, we are tinting the entire thing with a red color. If I set this to white and run this again, now we can see it much better. We're getting a gradient and a red top, which might not have been what you expected. That is because when we are defining the cylinder, this mesh, then we are creating a 3D object. But when we are creating the texture, we are creating a 2D object. And Raylib doesn't really know where to put 2D image pieces on a 3D space. For that, we would need what is called a UV map. What that means is basically we are taking a 3D model and we are laying it out on a 2D space, so that basically every single face of the model is flat. And that means, for example, if we have a globe, we can get a flat representation and then assign a texture to it. That way, Raylib knows where to put one part of the texture for specific faces. Something that we cannot really do by default inside of Raylib. For that, you would want to use a program like Blender, which can do it quite easily. But not really a problem that we have to deal with right now. So with that, we have a texture and we have models that we can work with. The last thing that I want to cover really quickly is going to be movement. In the most basic sense. Let me add another section for movement. I want to create a position, which is going to be a vector 3 for this cylinder that we have just created. Which means this vector 3 should be the position. The end result is going to look the same. But now what we can do before we are doing any of the drawing, I want to get position and then target one of the axes. Let's say X. To that, I want to add 2 times delta time. If I run this now, we are moving the shape. That looks pretty good. And I can see X is basically going left and right. If we did the same thing to Y, we would be going up and down. And if we targeted Z, we would go forward and backward. That's pretty much it. What you can also do is get the model cylinder in my case, and then target transform. This could rotate and scale the model among a few other things. What you always want in here is a matrix, and then you have rotate at, there's also scale in there somewhere, scale. You can do quite a few things in here. For example, what you could do is rotate X, for which we want to have an angle. If I set this to 30 degrees, we are rotating around the x-axis. That would be this axis here. You could also animate all of this by setting a rotation with a default value of 0, and then increase the rotation amount by plus equal, let's say 4 times delta time, and then use that rotation value. With that, we are getting an animated rotation. Pretty easy. And alright, I think that's a pretty good start for the basics of 3D game development. Now that we have basic shapes and the general logic of 3D game development, we can import models, which are going to look significantly better. This part is also fairly simple, although there are a couple of issues that could come up and be quite annoying. I guess the one thing that I want to talk about right away is 3D object file formats. When you look around for 3D objects, you can find a lot of file formats. There's OBJ, FBX, GLB, GLTF, and quite a few more. And just to demonstrate, here once again, we are in Blender. This ship I'm going to import into Raylib in just a second. But first of all, what we can do in Blender is go to File, Export, and then we get all of the export options that we have. All of these are valid 3D file formats. Although arguably some of those are a bit weird, like SVG and PDF, those don't really count. But still, you have lots of options which can be quite confusing. And as a general rule of thumb, you want to use either GLB or GLTF files. Both are totally fine. In fact, they are basically the same format. Via this file type, you can contain a shape, so a mesh, textures, and even animations. On top of that, it's entirely free, so you don't have to worry about any kind of payment. FBX is a really powerful file format that you also see very often, but the downside is that it's proprietary, meaning at some point, somewhere, somebody has to pay for it. OBJ is also very popular, but a very outdated and old format at this point, that is also not developed anymore. I have a new Python file called toImports.py, in which we do lots of familiar things. We have the imports, we are initializing a window, then we are creating a 3D camera, and finally, we have the drawing bits, in which at the moment, we are only drawing a basic grid. I guess on top of that, we're drawing a white background, but that's a fairly minor part. What we want to focus on are the imports. To be more precise, I want to look at models and then import these things. The easiest one would be ship.glb. That is what you have just seen. And to import it, all we need is first of all a variable to store it in, let's call it ship, and then load underscore model, for which we are going to need a file path, which means, once again, we want from os.path import join. Then we can use join to go to models, in which we have ship.glb. If I now run this, we are not getting an error message. That's a good sign. That means now, inside of the ship, we have a model, and we know how to display that. Inside of the 3D bit, we want to draw a model. For that, I want to have the ship. The position can be a vector of 3 with 0, 0, and 0. Scale can stay at 1. And then for tint, I want to go with white. If I now run this again, we can see the ship. That looks pretty good. So effectively, via this GLB format, we are getting the mesh along with a texture. It could also contain animations, but those I don't worry about for this tutorial. But well, that is pretty much it to import models. It's very, very simple. That being said, there are a couple of caveats that you want to keep in mind. The first one is, besides the ship, we have a rupee, which I also want to import, and keep in mind here, this is a GLTF file, which by itself is totally fine. In fact, let me copy this line. I want to import rupee.gltf and store it inside of a rupee variable. If I now draw the model, rupee, we can't see anything. And if that happens, you want to look at the terminal. Somewhere in there, we're getting a warning that Raylib cannot find a mesh or a material. The reason for that is that I simply have a typo in the path. This should be GLTF. If I run this again, now we can see the rupee. That's a really good sign. That still works just as expected. However, if you look at the file explorer, we have rupee GLTF, we have rupee red.bin, and we have nagon texture.png. We need all three for the full rupee. And to visualize, let me get rid of the texture. If I delete this one for now and try the same code again, then the rupee is going to be white, which is a bit hard to see. Let me change the background to black. They can see this a bit better. Let's undo all of this actually. I do want to have the texture inside of this folder. This is something that can be a bit annoying for 3D objects. Sometimes everything is contained inside of a single file. Other times, you have the file and then a texture separately. All of this is determined when the file was created. So if you work in a team, you really want to talk to the artist. That's super important. In fact, this Ruby red bin file, if you get rid of it and try to run all of this again, the game is just going to crash. Which means I really want to keep the bin file as well. For the Ruby, you simply need all three of them. That's one common pitfall. For the Ruby, you need the texture and bin file must be there. Just always keep that in mind. Besides that, we have one more GLB file called shipfail.glb. This is a bit of a trap. I can import this like we have done before. Although this I want to store inside of shipfail, and we also need to update the path. This should be shipfail.glb. If I try to display this one, shipfail, I can run the code, and we cannot see anything. This we have already seen with the Ruby. But now, if you look at the terminal, we do not get any kind of warning. Raylib could find the texture and the mesh. So why can't we see the ship? If I open this file inside of Blender, you can see that here we have the origin, and the ship is really far away from that. That is another thing that is kind of annoying in 3D files. The position of the object relative to the origin is included in the file. Or in other words, back inside of a Raylib, if I zoom out far enough, we should be able to see the ship itself. Let's change this to 50 and 50 for the camera position. And if I try this again, you can see the ship is there. It's just not drawn in the center, where I would expect it. So just keep that in mind. It can be a really annoying mistake. This file is simply far from origin point. Finally, there's one more error that you want to keep in mind. For that, I want to draw the ship again, like so. And this one worked as before, although we are quite far away with the camera. Let's change this back to 5 and 5. There we go. We have our ship. That works, but if I scale up the ship, for which I want to get ship and then transform with matrix underscore scale, for which we need X, Y, and Z. If I scale all of this up by a factor of 10 and run the thing again, we can kind of see something in the top left. Here and here we have something, but we cannot see the ship anymore. And that is because for 3D objects, you can only see one side, which usually is the outside. If you had the camera inside of the ship, you wouldn't see anything because the insides are not rendered. This is the default behavior for any 3D object. This could be changed, but most of the time you don't want to do that because the inside of a 3D object aren't usually relevant. Just keep in mind, if your camera is inside of an object, you cannot see the object itself, which is another behavior that sometimes gets a bit annoying. But anyway, with that, we can import an object and we have covered some common errors. So I hope at this point you can import your own files just fine. For the next major part, I want to work on 3D collisions. Once again, a really important part of any 3D game, and it's going to be fairly similar compared to what we have seen in 2D. Or in other words, 3D collisions work a lot like 2D ones, in the sense that we are still using simple shapes. The only difference now is that instead of a circle we have a sphere, and instead of a rectangle we have a box. There are a few more minor differences, but those aren't too important. Which means we can work inside of VS Code right away, and I have a new Python file called freecollision.py. If I run this one, we are getting two spheres, and I can move the red one around using the keyboard. The way all of this works is we are doing the usual imports, and then we are setting up a window and a camera. After that, we are creating a player and an obstacle. Both of those are spheres, which we get by creating this mesh sphere. After that, inside of the loop, we are getting direction from the keyboard and using that to move the player. After that, we do all of the drawing. In there, we have the background, we are drawing a grid, and then we draw the player and the obstacle. That's pretty much it. Which means for now, I want to get a collision between two spheres. the player and the obstacle. To figure that one out, you want to look at the documentation and scroll down quite a bit until you reach our models. At the bottom of that part, you can find the 3D collision functions, which look fairly similar compared to the 2D ones. For example, we have, first of all, check collision spheres, for which we want a center and a radius for one sphere, and then another center and another radius for the other sphere. In our case, we know that from GenMesh sphere, we are getting a radius of 0.5 for both spheres. Although I guess to make this slightly more interesting, let's change the size of the obstacle to 2. That way, we are getting 2 different sizes. And now, for the collision, before we are doing any drawing, I want to check for collision, which I'm getting with check underscore collision underscore spheres. Then we need the player position and the radius, which for the player is 0.5, the number we have used here. After that, we need a second position, which in our case is the obstacle position, this one. And finally, an obstacle radius, which is 2. This is then going to return a boolean, which we can print. Let's try that. And now, if I run all of this, we're getting false without a collision, but once we have a collision, we're getting true. That is pretty straightforward. And this would be the easiest collision, where you simply do what you have done in 2D, except now you use a slightly different function. So this would be the simplest kind of collision mechanic. Besides that, if you want to check between boxes or boxes and spheres, you need what is called a bounding box. That bounding box is created via another function, which is called getMeshBoundingBox, which is returning a bounding box, and the only argument it wants is a mesh. Let's work with that. For the player, I don't want a sphere anymore. Instead, I want to GenMesh a cube, for which we are going to need another argument. Let's go with 1, 1, and 1 for all 3 dimensions. That way, now we are getting a box. And I want to know if this box is colliding with the sphere, for which we will need the bounding box. This I want to store in a variable. Let's call it bbox. The function we need is called getMeshBoundingBox, and in there I want to add the mesh we have just created. In our case, we have the mesh right inside of the model, meaning we would access it via player and meshes, with the index being 0. If I run this, we're not getting an error, so that looks pretty good. After we have that, we can look for another collision, which we get via check underscore collision. For this one, we are looking for a box sphere, for which first of all, we want to have a bounding box, which in our case is bbox, and then we want to have a center and a radius for a sphere. That we already have. It's the obstacle position and 2. The same thing we have done up here. This is going to return a boolean value once again, which we can print. Although if I now run all of this, we're getting false, even if the box collides with the sphere. So what's going wrong here? The issue is that this bounding box does not update. I can actually demonstrate that. If you look at the documentation once again, there we have draw bounding box, which is quite nice to visualize what's going on. Back in the code, I want to draw a bounding box, for which we need the bounding box first of all, and then we need a color. Let's go with green. If I now run the code, we are getting right in the center a bounding box, and the position of this bounding box does not update, which is what's causing all of the problems. The way you want to think about it is that the bounding box is simply a box around a mesh. It does not care about the position by default. To get that behavior, we need to modify things just a bit. An easy way of doing that would be via a function, let's call it getBoundingBox. For the parameters, I want to have a model and a position. So for example, when I'm using this function in just a second, I'm going to add the player and the player position. In here, first of all, I want to get the bounding box of the model for the general shape, which means get mesh bounding box with model and meshes 0. The same thing that we have done down here. Now, to actually use this bounding box, you have to understand how it works. And I think the best way for that is to print what you are actually getting. So I want to print the bounding box and then call the function. Instead of printing all of this, I want to get the bounding box function, the one I have just defined up here, and then pass in the player and the position. If I now run this again, we are getting a struct bounding box. To get a bit more insight into it, you want to print here of the bounding box, and then you get the actual parts of it. There are only two. We have max and min. Since we are defining a box, we only need 2 points, the top left and the bottom right. Or in other words, if I print bounding box dot min, this is going to be a vector 3, and on there I can get, for example, x. If I run this now, we're getting negative 0.5, which would be this position here. I suppose a better way of showing all of this is to print x, y, and z. Then you can see we get negative 5, and negative 5, which is going to be this top left point. That's the minimum point. And if we added in the maximum point, we would go down here, meaning the entirety of the bounding box is just these 2 points, which by default do not change. But what we could be doing is add the position of the player to them, and then we get an updated bounding box. Which means all that we really want to do is get a minimum boundary and then a maximum boundary. For both of those, we effectively want to add the position of the player to the bounding box.min and bounding box.max. Unfortunately, in Raylib, at least in the Python bindings, we cannot add those two vectors together. If we tried that, we will get an error. The way you are supposed to do that is via vector3 add. And then add those two as arguments. That way, you are adding vectors together in Raylib. It's a bit annoying, but well, it is what it is. Besides that, we want to have position.max. And that way, we are getting the minimum and the maximum boundary adjusted for the position, which we can then use to create a new bounding box that I want to return right away. For which, once again, we will need the minimum boundary and the maximum boundary. This would now be a bounding box that is adjusted for the position, which means I want to uncomment this collision box sphere check. And instead of the b box for the player, I want to call the function, which is returning a new bounding box. On top of that, when we are drawing the bounding box, I want to pass in the function with player and position once again. If I now run this again, we are getting the green outline of the player, that is the bounding box. And if I collide with the sphere, we are getting false and true whenever we have a collision. So that is working pretty well. And I hope all of this wasn't too confusing. Basically, get mesh bounding box is only giving you the shape of an object. For actual collisions, you have to combine this shape with the position of the object that you are looking at, which you do by getting the minimum boundary and add it to the position, and then same with maximum boundary, which you also want to add to the position. That's all you really need. That means, finally, we can look at a collision between two rectangles. For the obstacle, I want to get rid of the sphere and instead gen mesh cube with some kind of dimension. Let's go with 2, 1, and 4. If I run this again, we're getting some kind of rectangular object. The size doesn't really matter as long as it's a rectangle. The size doesn't really matter as long as we have some kind of cube. To get the collisions for this one, as always, I want to print the result. We want to check for collisions between boxes, for which we will need 2 bounding boxes that we can get very easily. The function we have already seen. We want to get the bounding box of the player with the player position. And besides that, I want to get the bounding box of the obstacle along with the obstacle position. If I run all of that, we're getting false without a collision and once we have a collision, we're getting true. So that part is also working pretty well. Cool. With that, we have basic collisions. And that system we can also use for collision resolution, which is going to be your exercise. I want you to implement a collision resolution system so that we are updating the position once we have a collision. For that, you can reuse basically all of the logic from the 2D system. You just have to apply to a 3D space. This isn't going to work perfectly right away, but try to implement the basics and see how far you get. So pause the video now and try this yourself. I want to contain all of the logic inside of a function. Let's call it check underscore collision, for which we are going to need an axis. For this project, we only have 2 meshes to worry about, which means I want to create 2 bounding boxes. One for the player, let's call it player B box, which we get via get bounding box with player and the player position. Besides that, I want to have the boundary B box, which we get from the obstacle and the obstacle position. This part should be obvious. We have to know the bounding box along with the position of all of the colliding objects. After we have that, I want to check if we have a check collision boxes with the player B box and the boundary B box. And if that is the case, I want to do something. For that, once again, we will need the logic that we have talked about in the 2D space, where first of all, we are separating the dimensions, which means for now, I only want to look at the x-axis. I guess we can add a pass in here, because besides that, I also want to check if axis is equal to z. For this one, I also at the moment don't want to do anything. Since we can't go up and down, we don't have to worry about y, although the logic for that would work in the same way. Like we have seen in 2D, when we are doing the actual movement, we are first moving in one direction, this time x, and then I want to check the collision on the x-axis. After we have that, we can do all of the z movement, and then we want to check the z collisions. First of all, I want to check the direction of the player, specifically direction.x. If that value is greater than 0, we know we are going to the right, which means position.x should be boundary bbox.min.x. This is not going to work perfectly yet, but we should get something. If I only move to the right, at some point the player is going to stop, although we are snapping into this position. What is happening here? Let me draw all of this actually, and we should be able to see the function as well. Boundary box minimum x is going to be this side here, effectively the left side of the bounding box. And as soon as we have a collision with the player moving to the right, then we are setting position.x of the player to this left side, which effectively means once this player touches this object, we are setting the center of the player to the left side of the object, which obviously isn't the intended goal. What we actually want to do is to move the right side of the player to the left side of the obstacle, which we can get by subtracting half the width of the player from this position. Since we know that the player has a size of 1, 1, and 1, all we have to do here is subtract 0.5. If I now run this again, we are touching the right side of the obstacle, and this works pretty well. That looks quite nice. That means besides that, we can cover the left movement, which means if direction.x is smaller than 0. If that's the case, once again, we want to update position.x and get boundary box, this time .max.x, and then add 0.5. With that, we still get this collision side, and if I now move to the other side, we also get collisions here. That looks really good. Next up for z, I basically want to do something very similar. If direction.z is greater than 0, if that is the case, I want to update position.z and get boundary box.min.z and subtract 0.5. Pretty much what we have done here, except on a different axis. This should work, but in practice it doesn't. So if I only go on one axis, let's say I go left and right, this works. And if I only go on z, This also works just fine. But if I now go down and left or right, then we are teleporting. The reason for that is if we only subtract 0.5, we are always going to have a collision, even if we go on another axis, which can be quite annoying. And the way around that is to simply add a very minor offset, let's say 0.01, to the player size that we are adjusting for. That way, all of this is going to work just fine again. And that looks pretty good. Finally, I want to check if direction.z is smaller than 0. If that is the case, position.z should be boundarybox.max.z plus 0.5001. That way, we should get all 4 of the sides. And that looks pretty solid. I'm quite aware that these kind of collision systems do get a bit more complex. I guess for now, at the very least, understand this bounding box system to get a position and a bounding box. If you understand that, doing this thing becomes much easier. Make sure to go through it step by step, then it becomes fairly doable. To finish up the basics of 3D game development, we have to talk about shaders, which in the most basic sense lets you do basic things like apply a grayscale filter or a flash filter to any object. Now shaders can do a lot more, but I want to keep it simple. In the most basic sense, a shader changes how a GPU draws textures and models, which in practice means you can use them to change the position and the color of pixels. Whenever the GPU draws anything, it goes through a whole number of steps. And some of these steps you can influence via a shader. The two important ones are vertex shaders and fragment shaders. A vertex shader happens fairly early. Via this shader, you can change where things are drawn. Later on in the pipeline, we have a fragment shader, and this one applies the color, which you can also change. Now, via that system, you can create really, really nice effects, and basically any kind of special effect in video games is done via a shader. The problem is that shaders get very complex very fast. Meaning for this tutorial, I will only show you how to use existing shaders. I will not cover how to create shaders from scratch. Although, if you want to create your own shaders, I guess a really good place to start would be inside of the Raylib website. There you have examples and a whole section on shaders, which gives you quite a bit of material to work with. For example, a really cool project is to create lights via shaders. There you can enable and disable various lights, which is pretty neat. Although, once again, this kind of project does get a lot more complex, so you have to spend a good amount of time on this. In our case though, we want to keep it a bit more simple. First of all, we have a new Python file called foreshader.py, in which we are drawing a really simple cylinder. For that, we are doing the usual imports. We are initializing a window and creating a camera. Then we are creating a model of a cylinder. Then we create a custom texture and apply it to the model. After that, we are drawing everything and we are also getting the key A input. Although at the moment, this doesn't do anything. This code should be super simple. Besides that, inside of the shaders folder, we have flash.fs and grayscale.fs. If you look at those, you get something slightly unfamiliar, although it shouldn't be too bad. Essentially, we are creating a whole bunch of variables, and then we are running a main function, in which we are updating some kind of color. For the flash shader, we want to color every single pixel white, so that we can create a flash on an object. For grayscale, this becomes a bit more complex, but once again, we are creating a whole bunch of variables, and then we run some logic, for which, once again, we are changing the color. For the grayscale filter, we want to apply, well, a grayscale. Once again, the logic here is going to be a separate tutorial. Don't worry too much about it, we simply want to use the existing shaders. For which, I want to add a section to the code, shaders. First of all, we have to load the shader and store it in a variable, for which I want to create a variable, shader, and then load underscore shader. Now we need two file paths. One for VS file name and another for FS file name. Via those, we are loading a vertex shader and a fragment shader. Or in other words, VS stands for vertex shader, FS stands for fragment shader. In our case, we are only going to use a fragment shader. As a consequence, the first argument should be null. And for Raylib, we have to use ffi.null. That is a Raylib way of saying that we don't want to have any value. After that, for the fragment shader, let's say I want to start with grayscale.fs, we will need a file path, for which, once again, I want from os.path import join. And then simply import the file, which means I want to go to shaders and then import grayscale.fs. That is all we need for now. If you now run the code, there shouldn't be an error message. In fact, if you look at the bottom, we have unloaded a shader successfully, and earlier we have gotten a shader compiled somewhere. Next up, we have to apply this shader to the material of the model, which we can do via the model. Then we want to get materials with 0. This is getting us the only material on this model at the moment. And to that, we can assign a shader. Since we only have one shader at the moment, I want to apply that one. If I now run the code, the model we have created is going to be in grayscale. Effectively, what happens is that we are creating a mesh and we are applying a texture with a color to it. The color at the moment is a gradient that goes from red to yellow. However, when we are drawing that model via the shader, we are telling the GPU to draw all of this only in grayscale colors. And that is what a shader does, which also makes them incredibly powerful. You could do a lot more logic in here to get really cool effects. Once again though, the math for that gets quite complex. So in our case, we want to keep it at that, where we can simply apply a shader. Although there's one more thing that we can do. If I load the flash shader via flash.fs, if I run that, we don't get any change. That is because inside of flash.fs, we have to update one variable, which at the moment is a vector2 flash. This variable I want to change from inside of the Python file. Specifically, whenever I'm pressing the A key, I want to set this value to a 1. Oh well, we have a vector2, so I want to set it to a vector2 with 1.0 and 0.0. If you look a bit further down, we are only using the x part of the vector anyway. For that, we have to add a few more minor things. First of all, we need to get the flash location. This we can get via get shader location, for which we first of all need the shader itself, and then the name of the uniform. A uniform inside of a shader is a variable that we can access from outside of the file. All we need here is the name of the variable, which I called flash. This name here. That gives us the location of the shader, and this should be spelled correctly, flash location. After we have that, we have to create an actual vector2 that we want to add to this vector. Unfortunately for this one, you couldn't simply create a vector2. Instead, let's call it the flash amount. You want to use, once again, FFI and then new. In here, you want to create a struct vector2 with an asterisk at the end. After that, via a list, you can assign the x and the y value, which by default, I want to set to 0 and 0. This is now giving us a vector2 that we can actually apply to the shader. All we need is set shader value with a whole bunch of arguments. First of all, the shader itself. After that, we need the location, which in our case was flash location. This is basically the variable we want to change. And then we need a value, flash amount in my case. Finally, we need a uniform type, or in other words, what kind of value we want to enter. In our case, we want to add a shader uniform vector2. This information you can get from the shader. We have a uniform vector2. And that is pretty much it. Although at the moment, if I run this, it shouldn't change anything. And it doesn't. That is because by default, these values are going to be 0 and 0. And when we create a new vector2, we get the same numbers. However, if I now change this number to a 1 and run this again, we are flashing everything white. And that you can also do only when a button is pressed inside of the game loop. If you're pressing A, I want to make the entire thing white. I can run this again, press A, and now we have a white object. So with that, you can load shaders and update variables inside of a shader. That's pretty much all you need to get started. Although once again, for this topic, you want to investigate a lot more. There are many things that you can do and many things that become quite complex. But anyway, with that, we have finished the 3D part. Finally, we can come to the 3D game and finish off this tutorial. Like with the 2D game, you should have all of the basic building blocks to make this thing yourself. Meaning the exercise for this part is going to be to create the entire thing on your own. Or at least try to get started and see how far you get. As a tip for the shadows, simply create semi-transparent cylinders. That's all I did. Although before getting started, inside of VS Code, you want to open the folder Game 3D. In there, we already have quite a few starting files. Let's have a look. We have 6 folders, and I think they're all fairly straightforward. Inside of the code folder, we have 3 files: main.py, settings.py, and the custom timer. The custom timer is just a timer, and settings.py has a couple of basic variables, nothing too complicated. Inside of main.py, we have a bit of logic, not very much. We have a game class, and in there, we are setting up the window and a camera. On top of that, we are importing a whole bunch of assets. If you open that method, we are actually doing quite a few things. We are importing 2 models for the player and the laser. Those are inside of the models folder. Then we are importing 3 audio files, like we have done in the 2D game. After that, we are getting a whole bunch of textures. All of those are simple 2D images with a pattern. Nothing special here. Finally, we are loading a font and giving it a font size. That way the entire thing looks much nicer. So nothing in here that is terribly complicated. Besides that, we have an update and a draw method that at the moment really don't do very much. To bring all of that together, we have the run method that actually runs the game. With all of that covered, if I run main.py, we are getting a plain black window that really doesn't do anything. This is the starting project. Use this to create the entirety of the 3D game. Pause the video now and see how far you get. I want to create a new Python file called models.py. In there, we are going to have all of the game objects. First of all, in there, I want from settings, import, everything. That way, we are getting all of this, most importantly, PyRay. Like we've done for 2D, I want to create a parent class called model, for which we will need a dunder init method with self, the actual model that we want to use, a position, the speed, and a direction. Although for this one, we can set a default value of vector 3 with 0, 0, and 0. All of these parameters we want to turn into attributes, meaning self.model is going to be model, self.pos is going to be the position, self.speed is speed, and finally self.direction will be direction. Besides that, I want to have a draw method which simply draws the model with the model attribute. In the position, scale can always be 1, and the tint color should always be white, the default values. Oh, and really important, I forgot, this should be self.model and self.position. Besides that, what I also want to create is an update method with self and delta time, in which we, for the parent class, only call self.move with delta time, which I guess we can create right away. Define move, which needs self and delta time. And all we want to do in here is update the position, meaning self.pos.x plus equal self.direction.x multiplied with self.speed and multiplied with delta time. This line I want to duplicate twice because besides x, I want to update y and z, for which I need self.direction.y and self.direction.z. This would be a very basic parent class, which we can then use to, for example, create, let's start with the easiest one, the floor. Once again, model is the parent class, and all the floor is going to do is to be, well, the floor. It doesn't have to move, it should just be below everything else and have some kind of texture. Inside of the dunder init method, I only want self and a texture. This texture, by the way, we are getting from this dark texture in just a second. First of all, though, we have to call super dunder init and get these parameters. Direction we can ignore because this one has a default value, which means we need model, position, and speed. Speed actually doesn't matter because the floor isn't supposed to move. This can be 0. Besides that, we are going to need a model, which I'm going to create via load model from mesh. The mesh I want to create is gen mesh cube with a size of 32, 1, and 32. You will see in a second why I've chosen those dimensions. For now, just go with it. Besides that, I want to call set material texture get model.materials with 0. To that, we can apply the texture, and then material map albedo. We want to change the color. To all of that, we want to apply the texture that we are getting from the parameter. That would give us the model with a texture. Finally, we need a position, which I guess we can do right away. I want to get vector 3 for now with 0, 0, and 0. We will change that in just a bit, so I want actual numbers in here. Once we have that, inside of main.py, first of all, I want from models import floor. And then inside of dunder init, I want to add a setup section, for which, first of all, we will need self.floor, which is going to be the floor with self.dark texture, which once again, we're getting from the import assets method down here. That means we now have a floor object, and on this floor object, we can call the draw method. We don't have to update it since it's not supposed to move. For that, once we are in the 3D mode, I want self.floor.draw. Let's try this, and we are getting a floor. That looks pretty good. I have chosen a dimension for this floor to cover the entire viewport. Although this doesn't work perfectly yet, because if you look in the top right and top left, we have some gaps. That is because in just a bit, I want to lower the floor so that the player can be on position 0 for Y, which I think makes the most sense. Which means the floor should be lowered just a bit, which we are doing by setting this vector 3 position, specifically the Y part, in my case to -2. If I do that, then we can see a lot more of the stuff behind the floor, which I do not want. To get rid of that, I want to move the floor a bit on the x-axis, 6.5, and on the z-axis, -8. With that, we cannot see the background anymore, and the floor is a bit lowered. That's actually all we need for the floor. So next up, to make all of this a bit more visual, I want to create the player, which is going to get its own class, player. I want to define, first of all, as always, a dunder init method. For the player, I always need self. Then we need a model and a shoot laser function, like we have seen in 2D. Once we have that, as always, super dunder init. And in there, we are going to need model, position, and speed. Model, we are getting from the parameters. The position is going to be vector 3 with 0, 0, and 0. For the speed, we can look at settings. Somewhere in there, we have player speed. This is what I want to use. And that would be the very basic player class. This we can use inside of main.py by first of all importing it. I want to create self.player and assign it player. for which we need two arguments, the model and shoot laser. The model is super easy. Once again, inside of import assets, we have self models and player. So self.models and then player. Besides that, we need a shoot laser method, which we are going to create in just a second. For now, self.shoot_laser. For that, I want to create define shoot_laser with self and a position. For now, we are simply going to print shoot laser. That is all we need to create a player and to display it inside of draw. After we are creating the floor, I want self.player.draw. Let's try this. And there we have the player. Looks pretty good. And now I can also demonstrate why we have to move the floor down by just a bit. If the floor Y position was 0, we wouldn't really see the player ship. Let's keep this at -2 and then keep on working inside of the player. I want to store shoot laser as an attribute, which means self.shoot_laser is going to be shoot laser. After that, I want to get player input, which means define input with self, and the player can only move on the x-axis. Or in other words, if I add pass in here and run this thing again, the player can only move this way or this way, which means the only direction that we have to update is self.direction.x, and the value we want is the integer of is_key down with key_right, and from that we want to subtract the same thing, except that we are looking at key left. That way we can move left and right. On top of that, I want to check if is key pressed with key_space. If we are pressing the space button, I want to shoot the laser, which means self.shoot_laser with some kind of position. For now, let's go with self.pos, the current position of the player. To use all of that, we want to override the update method of the parent class. Or in other words, inside of class model, I want to still do the move stuff, but then also get input. So in other words, I first of all want to call self.input and then do the parent stuff, super.update with delta time. That way, inside of main.py, I want self.player.update with delta time. And now I can move left and right. That is working really well. Perfect. To make all of that look a bit more appealing, I also want to rotate the player, for which, first of all, we will need self.angle. By default, this one will be 0. That value we are going to change inside of the update method. I want self.angle minus equal self.direction.x multiplied by 10 multiplied by delta time. If we are going in the x direction, we are rotating in the opposite direction. You will see in a second how that's going to work. Now, to make all of this actually visible, we also have to update the draw method. At the moment, we are simply using draw model, which cannot accept a rotation. So what I want to use instead is draw model x, which has a rotation part. For that though, first of all, we will need self.model for the model, self.pos for the position. Then we need a rotation axis, which needs to be a vector 3. I want this to be 0, 0, and 1. That way, we are rotating around the z-axis. After that, we need a rotation angle, which is self.angle. Then we need a scale, which has to be a vector 3, which in my case should be 1, 1, and 1. Finally, tint color, white. With all of that covered, if I move to the right, we are rotating the ship a bit in this direction. And if I go left, we are rotating the other way. That way, it feels a bit more 3D-ish. Besides draw model X, you could have also used transform with matrix rotate. Both would be acceptable, but since this rotation is fairly simple, I think this is the easier approach. Besides that, I want to set a few constraints for the rotation and the position. First of all, the position. Self.post.x should never get too negative or too positive. Or in other words, what we can do at the moment inside of the game is simply go all the way to the left or all the way to the right and then never stop. This I do want to change. I first of all want to get a minimum value, which I get via the max function with 0 and self.post.x. That way, x can never go below 0. Although that's not actually what I want. The lowest value should be -6. Besides that, for the maximum value, I want to use min, then self.position, and besides that, 7. That way, we can never go beyond 7 or below -6. Let's try all of that, and if I go to the right, at some point, we are going to stop, although the rotation is going to continue. Not ideal, but that we're going to fix in a second. Left side also works, so this is going well. For the rotation, I want self.angle and do pretty much the same thing. I want to go with max, then -15, then min with self.angle and +15. That way, at some point, we are reaching our maximum rotation, which I guess we could set a bit lower, but it's good enough. The player probably won't notice. As always, these things can be fine-tuned, but in my case, I don't really care so much. What I rather care about is to make the player look a bit nicer. Effectively what I want. Inside of the game, the player position on the y-axis, meaning up and down, should fluctuate, so the player goes up and down in intervals. For that, we need a sine wave. This we can import inside of models.py from math import sin. That way, we can create a sine wave. In case you don't know what that is, on a graph, we have x and y values, with x simply being the time. A sine wave basically looks something like this, where we are going in intervals between -1 and +1. I guess right below the angle, I want to update self.post.y. And then add the sine value, for which we need an x value, which we get via get time. And as always, whenever you do any kind of positional change, you want to multiply it with delta time. Now, this is not going to work yet. I think we have to fine-tune this, but we're getting something. Now the player is slowly moving up and down. Now, first of all, I don't want the player to move that much. So let's multiply the entire thing with 0.05. That way, we are only going up and down in very small numbers. Might be a bit too little. Let's go with 0.1. I guess that feels better. To make all of this faster, you want to multiply this value, in my case the time. For example, with 5, that way this should go a bit faster. And there we go. Now the player is going up and down at a reasonable pace. And that concludes the player. That's really all we need in here. Although to make the player look good, we also want to have a shadow, because right now you can't really tell that the player is that much on top of the floor. For that, inside of the game class, I want to create another method. Let's do it below the update stuff. Define, draw, shadows. No need for custom parameters. All we want to do in here is to, well, draw a bunch of cylinders. For the player, this is the easiest part. First of all, we will need a position, which in my case is going to be vector 3 with x, y, and z. X and z are going to be copied from the player, which means self.player.post.x. Then we need y, this comes in a second, and self.player.post.z. For y, we simply want to go a bit below the player. Since we know that the floor is at position -2, for the shadow, I want to go with -1.5. That gives us a position. Besides that, we need a radius top and a radius bottom. Those two values are going to be the same in my case, and for now, I want to have 0.5 for both. Then we need a height. This can be 0.1. That's not very important. Then we need slices to make sure this thing looks round. Let's go with 20. Finally, we need a color, and I guess to get started, let's go with black. That should be giving us a shadow, and this I want to draw before we are doing the player, although it shouldn't matter that much. Self.draw shadows. Let's try this again. And now, below the player, we have a shadow. Doesn't look amazing yet, but at least we get a bit more context in terms of where things are in 3D space. Can be a bit confusing sometimes. To make this shadow a bit more transparent, I want to set a custom color with 0, 0, and 0 for RGB, so we're getting black. But then for transparency, I want to go with 50. That way, this thing is quite transparent, which is definitely looking better. Besides that, to indicate that the player is going up and down from the sine wave stuff that we have done here, I want to scale the size of the shadow along with the player's Y position. I guess to keep all of this a bit more organized, let's create another variable, player radius. This should be 0.5 plus self.player.position.y. Since this value changes from the sine value, this value should also update. And that I want to use for the top and the bottom radius of the shadow. Let's try this one again. And now, if you look at the shadow, this thing grows and shrinks. That would be our first shadow, and we also have the player model. That looks good. Next up then, we can work on the laser. As always, this inherits from the model class, and then we need a bunch of things. The laser is actually super simple. We only need a dunder init method with self, a model, a position, and a texture. Then we want to initialize the parent class with super dunder init, where we are passing in the model, the position. Then we need a speed. This we're getting from settings. Somewhere in there, we have laser speed. After that, we need a direction, which is always going to be a vector 3 that goes 0, 0, and -1. Besides that, I want set material texture, then get self.model.materials with index 0, get material map albedo, and finally the texture. So we can apply custom color to the model. This we can use inside of main.py, first of all, by importing the thing. Import laser from models. To organize all of the lasers, I want to implement a similar system that we have seen for the 2D game. Which means I want self.lasers, and I guess while we're here, self.meteors. That's going to become important in a second. We want to have a list for each. And then, whenever the player shoots a laser, I want to create one instance of a laser and append it to the lasers list. Or in other words, self.lasers.append with one instance of the laser class, for which we are then going to need 3 arguments. A model, a position, and a texture. The position we are getting from the parameters, so that part is easy. The texture is also going to be easy, self., and I think I called this one light texture. This is what I want to use. You could also use a red or a green or orange texture, or even one of the dark ones, or set a custom color. It doesn't really matter. Just choose what you like. Besides that, we need a model. And this we are getting, once again, from import assets. There we have a laser. I can just copy what we have gotten from the player and change player to laser. With that, inside of the game, if I press space, nothing happens. And that is because we have to draw and update anything inside of lasers. Meaning inside of update, I want for model in self.lasers, and let's do it right away, plus self.meteors, and then model.update with delta time. The same thing we want to do inside of the draw method. I want for model and then all of this, but then model.draw without any arguments. And now if I run this, we are doing something weird. The player moves forward. What happened here? Basically, when we are creating a laser, we are passing the position into one of these laser classes. And then inside of that laser class, we are moving it forward. We are not creating a copy of the position. We are simply using the position for the player in the laser as well. And we are updating it along the way, which obviously shouldn't happen. What we instead want to do when we are shooting the laser, we want to pass in a copy of the player position. The thing we don't want to do is to pass in an actual reference to the player position. I guess one way of doing that is instead of getting self.position, I want to get vector 3 and then add a value, for which I need 2 vectors. I want to have self.position and then add another vector with 0, 0, and -1. That way we are moving up the starting position of the laser a bit forward, and this should be vector add with a capital A. Now let's try this again, and if I press space, we are getting a laser, and the ship doesn't move forward anymore. That looks pretty good. Now at this point, you could customize the logic so we cannot shoot as fast anymore, which does get a bit silly, but well, it's not too bad. Cool. With that, we are getting lasers. Next up then, inside of models, I want to create the meteors. Class meteor. With the same parent class and defined under init. All I want for the meteor is self and a texture, which is going to do quite a few things. So let's organize it via comments. First of all, I want to do the setup. Most importantly in here, super dunder init to initialize the parent class, for which we will need a model, a position, some kind of speed, and a direction. Speed and direction are fairly simple. This we have kind of seen in the 2D game. For speed, I want to get a random value within this meteor speed range. Or in other words, I want to get uniform and then unpack meteor speed range. I think in the 2D game we used randint, which we now don't want to use because we have 2 single-digit integers for the speed. Meaning I want to have a floating point value between those two, for which we need uniform. After that, the direction is going to be a vector 3. This can just be 0, 0, and 1. So we are going down the z-axis. I suppose you could customize it a bit more with uniform and then go from 0.75 to 1.25. After that, we need a model and a position. For the position, I want to create a separate variable and then vector 3 with x, y, and z, where z is always going to be -20 and y is going to be 0. For x, I want to have a uniform value between -6 and 7. The same values that we use to constrain the player. If I find it really quickly, these values here. I guess you could put those inside of settings to keep it a bit more organized, but it's not too bad. That gives us the position. Next up, we will need a model, for which, first of all, I want to have a radius. All of the meteors are going to be basic spheres. For this value, I want to have a uniform that can range between 0.6 and 1.5. From that radius, I want to create a model with load model from mesh and then generate a sphere via gen mesh sphere. For that, we need a radius that we already have, self.radius. And then we need rings and slices, which I have both set to 8. That's going to give us the model. And besides that, I want to set the material texture with model materials 0, material map albedo, and the texture that we are getting from the parameter. That's already quite a bit. Let's test if this is working. For that, inside of main.py, first of all, I want to import the meteor class and then create a timer to spawn meteors. which means I want to have self.meteor_timer once again, which is going to be a timer that we are getting from the custom timer class. I think I'm importing it inside of settings.py. There, we have the custom timer. For this class, first of all, we need a duration, which we are getting from settings. We have meteor timer duration. This timer should be repeated. It should auto start. And once it triggers, we want to call self.createMeteor, a method that does not exist at the moment, which means we want to define createMeteor. Like we have seen for the laser, we want to get self.meteors, the list we created a few minutes ago, and then append one instance of the meteor class, for which we are then going to need one argument, a texture. And for this game, after we have imported all of the textures, the colored ones, I want to pick one of those at random, for which we are going to use choice and then self.textures. And as a reminder, inside of textures, we are importing all of the textures with a color. Once we have that, we should already be drawing the meteors, because inside of update and draw, we're getting the lasers and the meteors. Let's try all of this now, and nothing happens. I think I know the reason why. We are not updating the meteor timer. For that, before we are doing anything else in the update loop, I want to get the meteor timer and update it. Next attempt. Now we are getting meteors. Not looking too bad. We can also still shoot a laser, so that is working reasonably well. Although these meteors look a bit stale right now, for that I want to add a few more things inside of their class. Most importantly, I want to add a rotation, for which we need to have a self.rotation vector, which has to be 3-dimensional, and then get some random values. In my case, I want to create 3 uniforms that all go from -5 to +5, meaning this value I want to copy and paste it 2 times. That way, we are getting a random x, y, and z value. Once we have that, we can override the update method of the parent while making sure that we are still calling it super update with delta time. And on top of that, I want self.model.transform, where we are setting a matrix rotate, and let's go with x, y, and z. All we have to add is a vector 3 with the rotation, which we already have, self.rotation. That way, if I run main.py again, so inside of the game now, we have all of these spheres being rotated, which already looks a lot more random. To animate all of that, I want to add another attribute, self.rotation_speed. This is also going to be a vector 3. Also, we are using uniform for random values, although those go from -1 to 1. This I want to have for x, y, and z. Let me copy and paste it 2 times. Next up, inside of the update method, I want to get self.rotation.x plus equal self.rotation_speed.x, and as always, multiplied with delta time. This I can duplicate to get rotation.y and rotation.z and rotation_speed.y along with rotation_speed.z. That should animate the entire thing. Let's try. And we are getting rotations. Perfect. That makes the entire thing feel much better. What is also going to help is to add shadows for all of the meteors. We have already seen this for the player. For the meteors, we are going to need a for loop for meteor in self.meteors. For each of those, we want to draw a cylinder where, first of all, we need a position, which, like for the player shadow, is going to be a vector 3 with meteor.pos.x, then y, which I guess we can set to -1.5 right away, and finally meteor.pos.z. After that, we need a radius, which can be the meteor.radius for the top and bottom part of the cylinder, which means I want to use meteor.radius twice. After that, we need the height of the cylinder, 0.1. Slices can be 20. And for the color, I want to use the same thing that we have used for the player shadow. Let me copy it. And then we should be getting something. Let's try this now. And for every single meteor, we are getting a shadow. That looks about alright. Arguably, these shadows are a bit large. If you want to modify that, all you have to do is to multiply the radius with, let's say, 0.9. That way, they should be a little bit smaller. I guess very slightly hard to see, but you get the idea. If you set this to 0.1, then the shadows are going to be really small, which looks a bit silly. Let's go with 0.8, and then we should have some reasonably sized shadows. That looks about alright. Now that we have lasers and meteors, we can work on the collisions, for which I want to add another method. Let's put it before the update method, define check underscore collisions. We want to have a player with meteor collision and a laser meteor collision. The player meteor collision is the easier one. Let's start here. All I want to do is for meteor in self.meteors, and then if check underscore collision spheres, for which we need a center and a radius for the player, and then a center and a radius for each meteor. To start with the player, self.player.pos, and for radius, I want to go with 1. For the meteor, then we want to have meteor.pos along with meteor.radius. Once we have that, I simply want to close the window to finish off the game. Let's try that one, which means inside of the update method, before we are doing anything else, I want to self.check collisions. If I now get hit by a meteor, let's go with the green one. The game is over, although I think there was still a bit of a distance between the ship and the meteor. So let's go with 0.8. That way, this should work a bit better. Let's collide with this one. And there, we had a collision. That gives us the first collision. Next up, for the laser meteor collision, we want 2 for loops. For laser in self.lasers, along with for meteor in self.meteors. For the laser, I want to have a bounding box, which means, first of all, I want to have the laser be box, which we get from get mesh bounding box with laser, model, and meshes 0. Don't forget, this bounding box of the laser does not include the position. This we have to add ourselves, for which I want to add a collision bounding box, which is going to be a bounding box that will need a minimum and a maximum value. For both of those, let's do this over multiple lines. I want to use vector3 add with laser bbbox.min and the laser.position. This would give us the minimum point. Besides that, I guess we can duplicate all of this. I want to have laser bbbox max and then the laser position again. This would give us the maximum point. That way we're getting a bounding box that respects the laser position. That I want to use with if check collision box sphere. The bounding box is going to be the collision bounding box. Then we need a center and a radius, which is going to be meteor.position and meteor.radius. If that happens to be the case, for now, let's simply print collision. Let's try. And if I shoot at a meteor at some point, we are getting collision. So that is working quite well. Perfect. Which means if this happens, I want to discard the meteor and the laser. Although for the meteor, I want to add a short flash for, let's say, 1/4 of a second. But let's start with the laser. All I want in here is get laser.discard and set it to true. With that, inside of the models, I guess we can add this to the main model. Inside of the init method, self.discard is going to be false by default. That way, we're getting discard inside of the laser and the meteor. I want to add another method inside of the game class define check discard. This is going to be the same logic that we have seen earlier, where I want to check self.lasers and then create a new list via list comprehension. Laser for laser in self.lasers, but only if not laser.discard. I suppose while we're here, we can do the same thing for the meteors, for which I simply want to replace laser with meteor. And this should be in self.meteors. This method we have to call inside of the update method. Right after doing the collisions, I want to check discard. That way, if a laser hits a meteor, it should disappear. And it does. That seems to be working quite well. Next up then for the meteor. If there's a collision with the laser, I want to stop the meteor, flash the meteor via a shader, and then destroy the meteor after a very short amount of time. A couple of things that we need. First of all, I want to get meteor.hit and set this one to true. This hit attribute doesn't exist yet, which means inside of the meteor, I want to add another section. I guess we can call this one the discard logic. For now, I only want to have self.hit in here, which by default will be false. Once we have that, inside of the update method, I only want to do anything in here if not self.hit. That way, inside of the game, once a laser hits a meteor, the meteor should stop doing anything, and that seems to be working. Perfect. Besides that, what we can do is add let's call it def timer, which is going to be a timer that we are getting once again from the custom timer. The duration should be 0.25 or a quarter of a second. It should not be repeated. It should not auto start. For the function, I want self-activate discard, which doesn't exist yet. So let's create activate discard. A super simple method, self.discard should be true. Also, to make sure that this timer is working, you have to call its update method. Before we're doing anything else inside of the update method, self.devtimer.update. With that, after we're hitting a meteor, it should stop moving and then disappear after a short amount of time, which doesn't happen yet. And that is because after the meteor gets hit, we are not starting the def timer. Remember, this one is not set to auto start. We want to get the meteor def timer and activate it. Let's try this again now. And if I hit a meteor, they stop moving, but that still doesn't do anything. And I think the reason is inside of check discard, this should be self.meteors, plural. So we're getting the list and not create a new attribute. Next attempt. If I now shoot at a meteor, it should disappear after a short amount. And that is working quite well. Perfect. The last thing I then want to do is to flash the meteor via meteor.flash, for which inside of the meteor, we are going to need a define flash, which for now is not going to do anything. Before this thing is going to work, we need to set up a shader, which I want to store in an attribute self.shader via load_shader. I only want to have a fragment shader, which means this is going to be ffi.null for the vertex shader, and for the fragment shader, I want to have join shaders, and the shader I want to import is called flash.fs, which is the only shader we have in the entire project. You might be wondering now, why do we import the shader when we are creating one instance of the meteor? Why don't we import the shader inside of import assets? If we did that, we would have one shader for every single object, which means if we updated the shader, it would update for every single instance of the meteors. As a consequence, we couldn't flash a single meteor, we would always flash all of the meteors at once. If, however, we load a shader for every single instance of a meteor, we can update the shader separately for every single object. This shader we have to apply via model.materials and 0. In there, we have a shader and we want self.shader. Besides that, we will need self.flashLocation via get shader location. I want to look at self.shader and get the flash uniform. In other words, if you look at the shader, we want to get this vector too. Finally, we will need self.flashAmount, where we are creating a vector 2 that we can actually pass into the shader. Via ffi.new, I want to create a struct vector2, and don't forget the asterisk. Then we need arguments. I want to have 0 and 1. Finally, whenever we are calling flash, I want to set the shader value where we are getting the shader with the flash location. After that, we want to have self.flashAmount. And finally, I want to have the shader uniform vector 2. That should be it. If I now hit a meteor, it should flash. Let's try. And this didn't work. For the error, I think I simply made a typo. This should be self.shader. Next attempt. Let's shoot at a meteor, and it flashes and then disappears. That looks really good. Nice, and with that, we have the entirety of the meteor logic. Next up, inside of main.py, I want to display the score for how long the player has been surviving. Let's put it right below draw shadows. I want to draw a score. First of all, for that, we will need the score itself, for which we want to get the time since the start of the project. This get time I want to turn into an integer, so we get cleaner numbers, and this integer I want to turn into a string. That way we can actually display some text. This I want to do via draw text x, where we can set a font, which we already have, self.font, that we're getting from import assets down here. Next up, we need the actual text, which in my case is the score. Then we need a position, which has to be a vector 2. For now, I guess I want to go with window width minus, and now if you look at settings, we have font padding. This I want to subtract from the window width and the window height. That way, we should be in the bottom righty bit. Afterwards, we need a font size, which we have as a font size constant inside of settings. This one here. Spacing is going to be 0, and the color is going to be white. This method we now have to call, which is going to happen inside of draw, but really important now, make sure you are doing this after your ending mode 3D. Only then do we want to draw the score. And as always, this should be self.drawScore. Let's try all of that, and in the bottom right, you can see we have something, but this doesn't work yet. And that is because font padding is too small. Let's change that to maybe 60. And then we can see in the bottom right, we have a score. Everything else still works just fine, so I am quite happy with that. We might need a bit more spacing between there, so maybe let's change this one to a 2. But this is just something that you can fine-tune, it's not too important. Righty, with that we have the score. That means the last thing that we have to work on is the sound, which we already have imported. In import assets, we have 3 audio files. Music for the background sound, and then a laser sound whenever we create a laser, and an explosion whenever a meteor gets hit. Let's start with the laser. Whenever the player is shooting a laser, I want to play a sound. Self.audio and laser. That part works. And next up, whenever there's a collision between a laser and a meteor, this happens down here. I want to play another sound, which I think I called explosion. Let's double check. Yeah, explosion. Next attempt. If I now hit a meteor, that also works. Finally then, for the background music, inside of Thunder Init, play a music stream with self.audio and music. This we have to update. Inside of the update method, I want to update the music stream with self.audio and music. And finally, once the game is over, we have to also unload the music stream. That should be it. Let's try the entire game now. Cool. And that is basically it. So I hope all of that was useful, and I'll see you around.